Well, good afternoon to everyone. My name is Alexis Guillot. I'm a French student in the second year of the Master of Artificial Intelligence at the University of Amsterdam. And I've just started my thesis with ESA in collaboration with Blackshore and 52 Impact. So let's get into it. What kind of problem am I trying to solve? So let's say that we have planet Earth, and on this planet there's some grasses, crop fields, etc. And we then have a satellite that will capture images of these. My goal is to build an algorithm that should be able to classify what kind of crops it is and whether there is a crop field at all. So let's look at this nice image taken by satellite, for example. I have access to this blue area, and I know exactly what kind of crop field is there and the kind of crops that is growing. And my goal is then to automatically label all the surroundings of even larger than this zone in red. So you may think, how do we do this? And this is where Blackshore comes in with this program called Cerberus. And they have this project that is basically, it's also like a city builder game. And in order to gain resources, you have to label on this interface, for example, what you see. And this is how we get the input data. So for example, that could be my training data in blue here, and I would use this to train my algorithm. So this is what it would look like, a more schematic way. On top, we have very high resolution images that are given to the players because it's more entertaining to play with better resolution images. It's about 50 centimeter spatial resolution. And then the players all together will label it. And it's actually been proven to be quite accurate on an expert level. So then using this architecture from 52 Impact, I have to come up with a way to automatically label the map. So natural question that arises is, where do we begin? Because the algorithm will not have the same parameters depending on the region you're working with. So our starting point would be Ethiopia, because it is known to be a country that produces a lot of crops like wheat and maize. And we're about to get exact coordinates of smallholders' farms in the region. And if it all goes well, then we can extend to Italy and surrounding regions. So yeah, however, one challenge that we face is that the crop calendars differs per crop. So the problem here, for example, is that we have to provide a single snapshot to the user because they're not going to label 20 different maps. So we have to choose really the right moment at which we have to figure out when we can better distinguish the crops and also distinguish visually what kind of crops is growing. So in order to test the algorithm, I'm going to use a Sentinel-2 data. And the nice thing about it is that it has 13 spectral bands, and since it's quite recent, there's been a few research using so many dimensions to build detection algorithm. So the spatial resolution will vary, but it's pretty much between 10 and 20 meters or 60 sometimes, depending on the band you're using. And the goal is then to play around with those bands and try to come up with one that will help the algorithm the best. So this is an example of the combination of bands with like RGB, but we have access to every kind of bands. So this is the second band, the third, seventh, which is a bit lower in resolution, as you can see, and the eighth, and so on. So in order to do that, we can gather some different measures like the normalized difference vegetation index or other combinations of band. So for example, below, this is the graph of this index for winter crops. So we need to know about the phenology of the phenology curve, so what the plant reflects back in order to be able to classify the crops and the kind of crops, because this value will vary quite a lot, both per crop and also during the life cycle of the plant. And this is an example where we can see on the left the normal image, and on the right it's the corresponding normalized index. And we can see that it's a tool that will for example, definitely help. And the goal is to come up with such indexes, for example, to classify better. So finally, this is what I have to come up with: a neural network that will take as input some bands or a combination of bands of the images, satellite imagery, and the according dimensions, and outputs in the end on the right the probability of each crop, and actually whether it's a crop field at all or not for each pixel. So yeah, that's it from my side. If you have any question, go ahead.
Yeah, excellent, beautiful presentation. Oh, nice.
Thank you.
Amazing. Yes. So, okay, any short question for Alexis?
I have a question.
Yeah.
Sure.
Alexis, that was fascinating. So is so I realized that you took the game as training data, if I understood you correctly.
Yes.
Would it be possible
correct.
to turn this whole thing into an AI enhanced citizen science project? Because I could think that people would love to play with reality in that way.
I think so. I think I can let Hans answer this question because he's the main person involved with this.
Excellent. So let's move to Hans because it goes logically to explain this game and activity that he founded under Blackshore Cerberus.
All right. Thanks, Alexis, for this awesome presentation. And I will just tell a little bit about our crowdsourcing platform. I won't go too deep. Well, my name is Hans van het Woud. I am director of the company Blackshore, and I'm actually the founder of the Cerberus crowdsourcing platform. And I started like 10 years ago with a game to help NASA scientists to map Mars based on Mars Reconnaissance Orbiter data. Now, 10 years ahead, collaborating a lot with the European Space Agency, we turned this platform in a platform to solve problems here on planet Earth, our own platform. And till now, we have like accumulated a crowd of 53,000 players, and they're all helping us to turn satellite imagery into knowledge, into maps. And with this, we are targeting to solve a multitude of world problems. But I will quickly share my screen. Now I need to share the right screen. That is the one. Well, you're all probably familiar with satellite images like this. This is an images captured by NASA's Mars Reconnaissance Orbiter, making pictures of Mars with a resolution of 25 centimeters. But with all this data, of course, there's a challenge. How do you turn this data into knowledge? How do you turn it into maps? Now, at the time I was writing my master thesis for the University of Amsterdam. I did a master human-centered multimedia, which is about like human-computer interaction. So I'm on the other side of artificial intelligence. I was really working on interaction between man and machine, man and computer. And well, I stumbled into this awesome Mars data, and I started to design something about this to solve a problem. And that is that a lot of Mars Reconnaissance Orbiter data, it is recorded, but who is going to look at the data? Who is going to turn it into maps? So what I did, I poured this Mars Reconnaissance Orbiter data in a game, in a computer game. At the time, it was still in Adobe Flash, and I asked players in this game, can you look for certain geological features of Mars, like certain type of sediments, type of wind erosion, anomalies. And the thing was that if a lot of people play this game together, we combine all of the data, we run some statistics, we get the output, and those are maps of Mars or of sections of Mars. What was really needed for this game? We needed two components. Of course, we need players to play the game because the crowd. It is a crowdsourcing platform, but to enable this crowd to do something useful, we must build in motivational elements. So game elements, it must be fun. It must be engaging. We need some bells and whistles to keep the game going. But what we also need are e-learning components. And before the crowd can map something, we must teach them something. So we must teach them a little bit about the geology of Mars. How do sediments work, or what types of wind erosion are there? And if we do this, the maps are like extremely reliable. And the nice thing is that the maps we generate, we are doing the same work as experts. The precision is the same. And the nice thing is, we are also mapping. So the precision is equal, and mapping is faster, and mapping is also more thorough. So if you have a lot of players, you cover a lot of ground. So that is about the Mars game. But at some point, I moved away from Mars, and I still want to build this Mars game or allow it to grow, but stimulated by the European Space Agency, we started to redesign this game and to run it to solve problems here back on Earth, like what Alexis is talking about, the issues in Ethiopia. So with this Mars ID, I ran into the European Space Business Incubation Center. They gave me a bag of money and, okay, Stan, can you start working on solving problems here back on Earth? And I started doing this. Like the first version of this game was to map disasters and to look at human crises. With this, turning this game into a disaster mapping game, I won a big European prize in 2012, the Copernicus Masters Prize. And it was like a very high resolution challenge because we are working very well with very high resolution, and it turned my company on the map and allowed me to start growing. This was the old Mars game.
Yes. Okay.
So and it was so that image is like an image of this is actually a training map based on Mars Reconnaissance Orbiter data, and like in this game you have to map certain features in a hexagonal field, so to say. So where do you think you see types of wind erosion or certain geological features? So, but I ended up in with ESA, of course. So here we are. So, and I opened my office in Noordwijk. Actually, I started at Aztec itself with my company. There I also met Bernard, of course. And from this point, this was like 2012, 11 was really the starting point of my company to where we are today. During this during this endeavor, building up my company, I got known for some reasons because people really like what we are doing with the crowd. One really fun thing was, you see it on the bottom right, actually, it was recorded at Aztec because at some point Bernard invited me also to become a crew member in the Mars Desert Research Station to be an analog astronaut for 2 weeks. And there we did a campaign, a Earth campaign to map planet Earth, as it were Mars, using my own crowd. So we asked the crowd to map a part of the desert in Utah, looking for geological features we can also see on Mars, like sediments or types of wind erosion. And in the station, we got coordinates generated by the crowd. So, we discovered something in the desert of Utah. And using those crowd-generated coordinates, we went out on our ATVs in our spacesuits, and to verify those coordinates. So it was an extremely high level of citizen science. The crowd was participating here on Earth, and the crowd was coordinating us as analog astronauts to do something real. So it was one of the nicest adventures in my life. And of course, it was really cool to be in the station and do all of the real crew things. Anyway, to go a little bit quicker, I will continue to where we are right now. I will show you one of the projects we're doing right now. So you see where the game is. Well, sorry, I will. How do I go to the nine? Hold on. Because we're doing, this is the one. Okay, so what are we doing right now? So we turned the platform into a platform to solve problems here back on Earth. And we're doing projects everywhere. And one nice thing is, for example, one project we did in Mali a few years ago, and that is to measure the positive economical impact of water pumps here on Earth. There's an NGO who has given water pumps to a certain region in Mali, and we want to know, okay, is it worth this investment? So we created a map on a certain area in Mali. So we trained the crowd. There's a demand. We want to look for houses, for water sources, fresh water sources, roads, things like this. And we asked the crowd, okay, can you start playing? And right now the game is in Unity. It is in 3D. It is always, we work with elevation data. And we asked the crowd, okay, can you look for houses in the game? And it's a little bit like Settlers of Catan. And we asked you to mark things in a hexagonal field. And like if I'm a player and I click on a house, I get a score for this, or I mark a house, and the higher the score is, the more other players are saying the same thing. So the more I do my best, the bigger the rewards. I get some virtual credits, and those credits I spend in a little shop for upgrades of the game. And all data combined is leading to a map. And the map is looking a little bit like this, what you see on the left. It is a map of 100 square kilometers generated by the crowd. You see this, for example, those ugly liver colors, and those are communities. And the nice thing is, if you put our map on top of Google, you see this, or on Bing Maps or other maps. And you see, actually, of this region, nothing is known. But there's a river in here because we found it. And there are roads, and there are people living there. So it proves that Google doesn't know everything. And the same thing for Bing Maps or OpenStreetMap. There's still a lot of work to do. And as for the game element, it is of course important to motivate the crowds. It must be fun and engaging. And in our maps, there are always interesting things to be discovered. Like here, this little aeroglyph you see. There's always in those regions in Africa some archaeological evidence, and we can give challenges to it. Like the first one who found the aeroglyph did win like an Xbox controller. Those are like the anomalies on Mars. We also have them. Anyway, to go back to Alexis, these hexagons, what we map, firstly, we are working on the generation of maps, but right now we are going to use these hexagons to act as training data for machine learning systems. So we are creating the best, the best balance between man and machine, and that we use this crowd to generate knowledge, and that machines can take over to monitor areas. And now we're even making a hybrid between using the crowd to map based on very high resolution, and then the machine trying to use this data to generate maps based on Sentinel-2 data, which is of high resolution data. So that's it in a nutshell.
Yeah, okay, excellent, a great story. So from Mars to the Earth, and with a lot of game fun. Yeah, okay, so this work that Alexis is doing, and also Samir that is going to talk, is done also in collaboration with 52 Impact. And so we have Amanda here from 52 Impact that can make a presentation. Amanda is well known from the EarthMoonMars team, as she has participated to the Luna campaign, and she's a geoscientist. And now she is also back to Earth, but from space. Yeah.
Oh, Bernard, thank you for the lovely introduction. So indeed, I'm Amanda, and I met Bernard when I started the Luna project. I studied planetary geology at the VU Amsterdam, because what is cooler than space rocks? And now I work for 52 Impact. And I would like to tell you something about the applications you can make by using space technology and how it provides insights to our changing Earth. Because we don't need machines to tell us that our Earth is changing and that we are leaving this really big human footprint. I mean, we feel the changing temperatures, we smell the air pollution, we see on the news or with our own eyes the ravaging fires and devastating storms. So experts agree that if we stay on this course, that the impact will be enormous. And we need to address this. And we can address this by monitoring and observing the Earth to identify critical regions and make a framework for future action. So we can gather a lot of information, not per se from looking up, but looking down from space. So we have this amazing number of satellites orbiting us. We are familiar with satellites providing our communication, that lead us home, the navigation satellites, or away from home, the ones that tell us what the weather will be like the coming days and weeks. And a really large group of satellites that's unknown to the general public is the ones that are used for Earth observation. And this market is expanding fast. While there were like in 2015, like 350 of these satellites, now this has at least doubled in size. And all these satellites are generating all this data, but what can we do? What can we do? Oh, I missed the slide. What can we do with all of this data? So the company I work for has many different products, and I will tell you quickly about 3 of them, not really about the theory, but what you can do with this satellite data. So the first one is 360 Blue. It's a software service that monitors water reservoirs and related risks. And it gathers Internet of Things data like temperature, turbidity, conductivity, or the chemical constituents of water, and combines this with satellite imagery, both radar and optical. And then you can make certain predictions, what is shown here in this dashboard. This is a watershed in Belo Horizonte in Brazil. And combining all these parameters, you can make predictions of, for example, how prone this area is to drought risks, or what the quality is of the water and what the water balance is. I mean, is this water reservoir replenishing or being depleted? And these kind of maps can be used by governments and businesses alike. Another one of our products is a dashboard we developed for the company Verstegen. And Verstegen wanted to have more insight in implementing agroforestry in their production cycle. So instead of growing a crop in a monoculture setting, implementing agriculture in agroforestry, so what's also referred to as regenerative farming. And satellite imagery, just like Alexis told us a little bit before, can tell us something about the state of a plant, how healthy it is, because plants reflect light at certain frequencies. And the more healthy, for example, a plant is, the more of it will absorb near infrared. And combining this with calculations on the change in plant quantity can tell us the change in biomass. And of course, from there, we can calculate how much carbon is stored, which is a hot topic at the moment, carbon sequestration. And also tell us something about how resilient this crop is to extreme weather, which is also, of course, very relevant in the near future. And I'm personally also very enthusiastic about this regenerative farming, because I really think this will help us in the transition towards a greener future. And putting concrete numbers on this project, yeah, I'm kind of enthusiastic about this. The last product I will tell about is our waste mapping product. So there are many ways to approach waste. We can, for example, take satellite imagery and put machine learning to it to find open dumps. But we can also create, for example, maps to indicate regions that are very prone to waste leakage. You can make a map where waste contamination can be very high due to a certain soil porosity or the groundwater depth, wind and rainfall data, and combine this with a map that tells us something about how much mismanaged waste there is, like this map shows in Mexico, because you can say how much waste there is produced on average, and then compare it to how much waste officially is picked up. You can make estimates on how much waste is mismanaged and therefore make maps indicating regions critical to waste leakage. But it doesn't end here. Satellites can tell us so much more, like air pollution. I mean, I think most of us have seen these maps by the space agencies that showed pre-COVID air quality and current air quality. You really could see the changes in chemical constituents, for example, emitted by airplanes. Another thing you can monitor is, of course, urban development. How do cities expand? How healthy is the green vegetation inside cities? Do we have heat islands? Also object detection, like crosswalks, hospitals, or the natural environment, coastal. Is there coastal degradation? How much suspended material is there flowing into the ocean? Sea temperature. We also monitored the development of an oil spill in Greece. So as you can see, there are really endless possibilities. And the beautiful thing, I think, that space technology really allows us to create insights from different perspectives, because satellites are not hindered by boundaries. You can zoom in on a 50-centimeter resolution or zoom out and see whole countries as big as China. And also by analyzing certain wavelengths, they can make the invisible visible for us, and a little bit predict the future by doing time series analysis. And in this way, of course, we can make more informed decisions and adjust policies if it's necessary, and I think it's necessary. But having this visual stimulation helps, of course. And it can also justify certificates, because when I buy my FSC wood or eat my MSC fish, it's so nice to have this sticker, but to have real-time monitoring on it would be even better. So it could assist in that as well. And personally, when I started working for 52 Impact, I discovered that I'm pretty passionate about using space technology to accelerate the sustainability efforts of businesses, large and small, because you can really enhance transparency into their production cycle and creating awareness about the operations and their consequences. And in this way, satellites space can motivate us and push the agenda for corporate responsibility. And well, this is our team. It's very small, but dedicated. We're housed in the Vanille Fabriek in Rotterdam. We on 52 degrees latitude, hence the name, 7 people since 2017. And we now have 2 great interns. So yeah, we always have nice projects lying around. So if you're interested, just shoot me an email or find us on LinkedIn.
Okay, excellent, Amanda. Thanks for the overview. Great presentation. Also, great issues how we are going to contribute to sustainable goals with smart skills. Okay, yeah. So I think this is a good direct transition to ask Samir to present his research on monitoring urban.
Yes, my thesis will be about monitoring temporal changes in urban areas using deep learning. First, let me introduce myself. I'm Samir, 22 years old, studying at the University of Amsterdam, studying artificial intelligence. I've also done my bachelor in AI over there. So let's get started. So yeah, in the title, I just want to explain this to the people who are not familiar with machine learning or deep learning. So this, I'm not a really big fan of this kind of diagrams, but in the sake of time, I will just try to explain a little bit what machine learning and deep learning is. So consider this input image of a car. In traditional machine learning tries to find patterns in your data and try to make a prediction out of that. And it does so by automatically learning without learning it by itself. So in traditional machine learning, you have your input image, which then is pre-processed. So you maybe normalize your image, you do some other stuff with it. Then in traditional machine learning, you extract features which you know beforehand. So let's say we are trying to classify cars over here, some images in car or not. We know that wheels or lights on the front and lights on the back are kind of characteristics for a car. So we add those, we extract those features from the image, input it in some kind of classification model and get our output. In deep learning, this feature extraction step is itself. So we are not explicitly telling look for the tires or look for the lights and that kind of stuff. It just tries to find them themselves. So that's pretty amazing. But on the other hand, it's also, it could have its disadvantages, because when we have a big data set of only orange cars, it thinks it may think that orange is one of the characteristics of a car, which is it's not the case. So yeah, that was in a very short time what it is. So so what are we looking for in a satellite image? So my title was looking for temporal changes what defines an urban area. And from papers that I read this, that an urban area, so first of all, what can you see from this image is you see green area, you see water, and you see buildings, and that are the characteristics of an urban area. So we are looking at the temporal changes over time. So we want to look at images from cities, in particular in Europe. So let's say this is Amsterdam for the people who did not recognize it. We want to look at different images at different timestamps and then monitor what's increasing and what's decreasing. And what we're monitoring right now are the three characteristics on the right top of the screen. Okay, so yeah, how to detect these temporal changes. So this is an example from a paper I read. What they're doing is, first of all, when you have the big image, like I showed you before, the big image, you first create tiles, smaller images, which are used in your algorithm. So you loop over the whole pictures in smaller tiles. And what they did was on the left image, you see two green squares, and that was green, and that was taken in 2016. It was like green forest land. And they saw that 2 years later that green forest land changed into something else, which looks like agricultural land or something like that, but it's not green anymore. So that's one way to detect by just classifying the images, and yes, so just by classifying the images. On the other hand, we see on the left side, we see some industrial buildings which are removed 1 year later. So this is one type of looking at the temporal changes. So saying something was there and it's not here anymore. But this gives a pretty good overview of the changes in urban areas, but this is not really, we want it to be more, I wanted it to be more finely. So what you can do is try to look at that specific region and tell, like, this region increased, the green area in this region increased or decreased by so much. So how do you do that? That is by, yes, so you try to segment the image in different image parts. Instead of saying, hey, I see some green area over here, you try to extract that from the image itself. So this is called image segmentation. And as you can imagine, you have a much more fine-grained view of the temporal changes by just saying, hey, there was an industrial building over here, but it's not here anymore. You can say, for example, from farmland, like farmland has decreased so much in this amount of time. So this method would be much more precise. Okay. So yeah, how does a pipeline look like? So as I explained, you have an image, you have different timestamps of an image of a city, for example. You go over it by smaller tiles that goes into your model, and that gives you a classification.
Excellent. So that was the overview of some of our Earth observation program. You see that's a lot of great things. And I want also to thank Thijs, that is a part of 52 Impact, that is co-supervising this student project. So now we go from Earth to a bit further because we are going to see images almost of exoplanets. So we have started a collaboration with also Amsterdam AI department, and we have had Victoria that finished her master, and now we have Ike and Christophe there, and we have also Johanna that is working on exoplanet work. So let's see, can you get some nice images of exoplanet, or at least get their size? Ike, the floor is yours.
Thank you, Bernard. I hope you can all hear me and see the slides. If not, just interrupt me.
Now we do, yes, good.
So my name is Ike. I'm a master student artificial intelligence at the University of Amsterdam as well. And currently I'm writing my thesis at ESA. So my research will partly build on Victoria's work. And she will, as Bernard said, also give a talk later. And my focus will mainly be on the detection of planets around stars where there's already a planet detected. And specifically, I will look at TESS data. So first of all, what is TESS? TESS is this space-based observatory that you can see in the image. And it was launched 2 years ago. And you can see it kind of as a replacement of the Kepler telescope. But whereas Kepler looked at a specific patch in the sky for a very long time, TESS was designed to search for exoplanets in the whole sky in the solar region around bright stars. But how do you find exoplanets? Well, what TESS does, it measures the brightness of thousands of stars at the same time over time. And when there is a planet orbiting the star, and it just so happens that the planet moves in front of the star, it blocks the light that's coming from the star towards us, and you can see a dip in the brightness. So, but in order for this to happen, you need to have the system being oriented edge on, and this makes it an unlikely event. But if you do have a planet detected this way, you already know the system is edge on. So it's a wise choice to look in the same system for additional planets, because if there are additional planets, they're likely to also transit. So we want to search through that data to find maybe more undetected planets. And why do we want to do that? Well, because with 2 planets, you know a lot more about the dynamics of the system than you know if you only know 1 planet. And maybe more importantly, you just want to find more Earth-like planets because, well, in the end, we want to find life elsewhere in the universe, maybe. But this light curve that I show here in the bottom, it's an oversimplification of the problem because in general, light curves are very noisy. So here you have a light curve of TESS of a specific star, and there's gaps, there is a whole bunch of noise, and there's outliers, and I'm sure no one of you, and neither can I, can tell where the transits are happening in this light curve. But actually, there are 3 distinct planets identified in this light curve, shown here in the bottom. So you can already see this is very hard to see with your naked eye, but you have some methods to do this, of course. And this light curve actually is from a star that's relatively quiet still, because it's quite flat, right? So this changes, and this gets more complicated if you have a star that's rotating around its own axis and has some stellar spots that are less bright. So you have this kind of wavy pattern in your light curve. And also you have these solar flares or stellar flares that make your star look a lot brighter suddenly. And this makes it very complicated. So in order to detect some planets, you really need to understand the physical processes behind it, and you need to model the noise in your light curve in order to find the transits. And Victoria is going to explain more in detail how she used some nice models to, well, fit these kind of curves and then characterize a planet system. And my research will mainly be about can we use this model, or can we maybe improve this model to model the stellar noise subtracted from the light curve to maybe detect some unseen small planets. And that's what I'll be focusing on for my thesis. And I'm only 4 weeks in, so I read mostly literature, and in the next months I'm gonna experiment a bit more. Yeah, so Victoria will later tell a bit more about the specific models that she used. And yeah, I gave you a bit of a high-level overview of the topic because I was the first exoplanet presentation, but my colleagues will dive a bit more in detail about their research. So thank you for listening.
Excellent, nice coordination within the team. And it was also nice to meet you at one of our EarthMoonMars workshop event that we had in Leiden, also because you are also an astronomer at heart. Huh? So
yes,
let's ask Christophe now. Yes, okay. So looking at anomalies in the transit light curves. Yeah.
Exactly. So, hello everyone. My name's Christophe Hunes. I'm also a AI master student from the University of Amsterdam, and yeah, I'm going to look a little bit closer at some special cases of light curves. Yeah, so Ike already explained the basics, and now I'm going to tell a little bit about my research. Yeah. So it's motivated by the question if there is something more than just usual exoplanets out there. And the answer is yes, there's a lot more interesting stuff happening. So unusual light curves can give a hint of interesting phenomena. And that's what I will try to find in my project. So this is an example of a light curve that's somewhat special. So the red line indicates how a regular exoplanet transit would look like, and the blue line, which better fits the data, yeah, is a special kind of transit. And this shows that sometimes you have to look very close because the differences to regular transits can be very subtle. And so for thousands of stars to look by this with your naked eye, with human eyes, that's not really feasible to do. So the idea was to apply AI methods that can automate this process and detect and maybe also characterize some of those special cases. Yeah, exactly. So I want to show you some examples of special cases. So the first one is disintegrating exoplanets or exocomets that also have similar transit shapes. So on the left-hand side, you see an image how this could look in real life. And on the right hand, you see a transit light curve that would be resulting from this phenomenon. So the red line, again, would show a regular planet transit. And this blue curve, which better fits the data, is more suitable for disintegrating exoplanets. So as you can see, in the end, there is some exponential decay of the effect, which is due to the tail of the disintegrating planets. So this happens when the radiation of the star dissolves the planet because it's simply so hot and yeah, destroys the planet basically. So it drags the dust tail behind the planet. Yeah, okay. Yeah, the second example I wanted to present you is called gravity darkening. So that's also very interesting, and that happens usually when you have a star that's rotating very quickly around its own axis. So by the centrifugal force, it gets squished together a little bit. So it's not shaped like a ball anymore, but more like an ellipsoid. As the poles are pushed together, they are hotter and the equator gets pushed away. It's cooler on the surface. So that also changes the appearance. So around the equator, you have like a dimmer belt. And on the right side, you can see how this could affect the light curve. So if the planet is first entering the transit on a hot pole, then you have like a deep dip in the flux. And then when it passes like this dimmer belt in the center, then you have this bulge in the middle of the light curve, which happens because the planet then blocks less light than it does at the hotter poles. Yeah, so the last example is the most common one, which is just stellar activity. So in particular, this example shows you sunspots or star spots like cold or cold spots. And so when a planet moves over some hot area, it blocks more lights. So then you also get a deeper, increase in the amount of light that's blocked. And the other way around, if you have a cold spot, then you block less light. And this can lead in weird shaped transits like you can see on the right. And by observing multiple transits of the same planet, for example, you can get an idea how the stellar surface may also change over time. And yeah, that's also an example. So overall, the idea is to first classify different kinds of special transit shapes, and then maybe apply a more more suitable model that's tailored to this problem to better estimate the stellar and planetary parameters.
Yeah, so this is great. And by the way, we start to see sunspot now. I was just observing yesterday, and actually there's one at the limb. And at the limb, you can also see around some brighter region. And so, so it's good also to observe our own sun to understand what happened on stars and reversely. Now, okay, we have Victoria on work on the exoplanet transit and stellar activity.
Hello, everyone. So yeah, I think this is a good transition because Christoph just talked about stellar activity, and that was one of the main focuses of my thesis research. So I'm Victoria. I just graduated from the AI program at the University of Amsterdam about a month ago. And my thesis topic was about characterizing exoplanet transits and stellar activity with scalable Gaussian processes. So this is quite a lot of terms in this title. So let me break it down. Basically, exoplanet transits and stellar activity are signals that I wanted to study in the light curves, and Gaussian processes were an AI method that I used to study them. So when I talked about characterizing these signals, what I mean is that I want to find accurate parameters that describe these signals. And I focus on two types of signals. The first is the exoplanet transits, which you can see on the left. And these are periodic dips in brightness caused by the planet passing in front of the star as it orbits. And these transits can be characterized by various transit parameters, such as the period, which is how frequently it orbits, or the depth, how much light it blocks. And from that, you can get very interesting information about the planet, like the radius, which is very important for determining whether it's a rocky planet or more like gas-like planet. And on the right, you can see that this is another signal I studied, the stellar activity, which is caused by magnetic activity on the surface of a star. And it creates this kind of wave-like signal. And from the signal, you can describe it with various parameters, such as a period, which tells you how fast the star is rotating, and which can also provide interesting information about how old it is and how active it is. Okay, so there were three questions driving my research. The first was, how well can this AI method characterize the stellar activity? The second was, how well can the AI method characterize the transit? So you can see that in the figures on the bottom. And then my third question was, when I model these together, does it lead to better overall characterization? And this is the algorithm that I use to characterize the transits and the stellar activity. And there is quite a lot of steps in the algorithm. So first I corrected the instrumental effects from the light curves. And then in the second stage, I made initial guesses of the parameters using traditional physics techniques. Then in the third step, I used the Gaussian process AI method to model the stellar activity and the exoplanet transits. And then finally, because I wanted more than just a point estimate for the parameters, I wanted an uncertainty interval. I had to use Markov chain Monte Carlo sampling to sample from the model and get these kind of parameter intervals. So I applied this algorithm to 9 stars observed by the Kepler mission and 15 stars observed by the TESS mission. And here's an example of some of the data that I analyzed. So here you can see kind of the rotation patterns and the signals from the planet as well. So in conclusion, the contributions of my thesis was that I answered the 3 original research questions. The first one, which was about stellar activity, I showed that my method was able to find all the very clear rotation periods for the stars, and it was able to find periods ranging from a third of a day to as long as 30 days. I also was able to find 4 rotation periods which were a bit more unclear and which other astronomers had struggled to find. Then for the second research question, which was more about the transits, I demonstrated that my method was able to find the radii of the planets within 1 sigma for all the Kepler planets and all but 2 TESS planets. And my method was able to do that for various sizes, so even small super Earths all the way to large Jupiters. And then finally, for the main question about whether modeling everything together improved the results, it was only the case for some stars. In general, having just a part modeling the background noise was already effective enough to get good planet parameters. And yeah, that's the end of my talk.
Okay, excellent. Yeah, of course, it's important to know the size of a planet. If the Earth would be 10% bigger, it would have evolved very differently. Maybe we would not be here. So when we look for those planets, these parameters are key. So let's move to Johanna, that is also part of the exoplanet group, and analyzing data, but also looking at making observations.
Yes, hello. I'm Johanna. I'm a bachelor student at Amsterdam University College, where I focus on physics. And I've been doing an internship with Bernard 1 day a week, where I look at test data, and I'm now using ground-based observatories to gather more data. So I'm now looking at one specific star to use from a ground-based observatory. This is WASP 140b. It's a star that Victoria also analyzed using her code. It's orbited very close to its star and is a very short period, highly eccentric. It is Jupiter mass star, a hot Jupiter to be precise, but as you can see, the exact radius isn't very well constrained. So we can improve on that maybe. Yeah. So here's the data that you get from TESS. I think Victoria seen this as well. So you can see that there's a clear rotation period, as you can see the curves in the data that we saw as well before in her talk. And you can look at this data you can fold it in half by looking at the period of the transit and the period of rotation to get a clearer idea of the transit signal and the rotation period, as I've done here. As you can see, it has a pretty clear transit signal. The rotation period, however, is a bit more unclear, but still quite good. And then I also was doing some further analysis on this star. You can see here that there's peaks at the frequency of about 1 microhertz, which corresponds to the rotation period of the star as well. You can see that in this analysis. And then there's also a power excess at about 200 microhertz or 300 microhertz. I'm looking more into that. It could be due to internal oscillations within the star. So now moving on to the ground-based observation that I'll be doing. So I'll be using the Las Cambas Observatory Network. So it's a network that has telescopes all over the world, as you can see here, which means that when you schedule an observation, they can do it from any of these telescopes. So there will always be a telescope that can observe your target. And this WASP 140 for me will be observed by the Siding Spring Observatory in Australia by 40 centimeter telescope. It's a robotic network, so the observations will be done automatically and sent to me straight away. And then some more details on the observation I'll be doing. So the star is a K-type star, which means it's more infrared light or more reddish light, and it's quite dim. So I'm using a red filter to get some new information, and probably it will be brighter in that filter as well. This filter, not as far as I can see from literature, has not been used before to observe this star. So we'll get some new information and perhaps get some better restraints on some of the parameters. And in general, we get a very close look at the transit, because for test data, it only looks every 2 minutes, but we can look at the transit in a lot more detail by looking a lot more often. And hopefully we can improve the characterization of this star. And this observation will happen tomorrow, hopefully. I already scheduled it before, but then the weather stopped it. But if all goes well, it should be happening tomorrow.
Exciting, yes. So we are getting to new data because, okay, some of our prospects to use our own telescopes here in Holland or to do a trip ourselves didn't work so well. So I think you found a very clever way to have access to many telescopes. So the one in Africa is in fact in Canarias, huh? So it's part of a bit off the coast, but on the map. Yeah, excellent. So this is also a good exercise that maybe we can use the experience of Johanna, also ourselves, to plan other type of observation of the sky, and after she gets some of the data. I see that that's a bravo to the exoplanet group. You were exactly in your time slot, very well coordinated. And so we have a regular meeting actually on the Tuesday morning with a group. And also on Friday, we have a meeting with Anna Eras Pastor. She's in fact the project scientist for the Plateau mission. So so we have a good collaboration with some colleagues from ESTEC as well. So yes, we are looking for more results. And so let's transit now from this very far world, exoplanet, to much closer to us. And so we have now a little session on Moon and Mars data. So who wants to start? So we can have so should we?
I can start.
Iris, we start with Mars, and then we'll go to the Moon with Jordan. Yes, excellent.
So I'm Iris. I'm a physics bachelor student from Amsterdam University College. And I've started doing this internship under supervision of Bernard in September. And for this internship, I'm studying the Martian climate, and I'm comparing the geomorphology of Mars with climate model predictions for a high obliquity. So as we all know, we're very much interested in finding water on Mars, especially flowing water. And there's an abundance of valleys on Mars, as you can see in the map on the right. And this shows to us that there must have been flowing water on Mars before in the past. However, when we use climate models to simulate the temperatures back in the past, we always get temperatures below freezing point. Even if we get temperatures above 0 Celsius degrees, because of the low atmospheric pressure on Mars, this is still below the freezing point for water, as this depends on pressure. So this leads us to consider subglacial rivers, which are river systems below glaciers. And because of the pressure of glaciers on basically the bottom of the glacier, the water ice in the glacier can start to melt and turn into fluid water, and thereby create these or erode these valleys. And also because of this glacier on top of the water doesn't come into contact with the atmosphere, so the atmospheric pressure is not important. And so papers have found that we can find glaciers at high obliquity, and obliquity is really like the skewedness of the actual tilt, so like the actual tilt of the planet. And a high obliquity leads to a high humidity, so a high water content into the atmosphere, which you need in order to create glaciers. And also, which is very important, is that it changes the circulation. Right now, in our current situation, we only have glaciers at the poles of Mars. However, as you saw in this picture before, there are valleys all over Mars, so the glaciers must have been very widespread. This changed circulation actually at high obliquity actually leads to air with a high water content being transported to the tropics and mid-latitudes of Mars, and thereby water can finally stay there, and it kind of gets stuck there through a circulation method. And thereby glaciers can probably form at high obliquity. However, research has only been done for an obliquity of 45 degrees at maximum, and I'll be looking at a higher obliquity of 60 degrees. So yeah, I'm looking into the possibility of subglacial rivers as an explanation for this widespread pattern of valleys. And so far, I made a map of the geomorphology of the valleys, and which includes the glacial landforms and a lot of specified valleys. Not all valleys as of yet have been specified, but some have been specified as an erosion style of glacial, subglacial, or fluvial, but that could also be subglacial. It's very undetermined yet. So you can see those on that map. And I'll be comparing those with climate models for a high obliquity of 60 degrees. And that's what I'll be focusing on for the rest. Thank you for listening.
Yes, okay, so Mars is okay, exciting, and so water under glaciers, yes, could be liquid. Yes, excellent. So clearly you have also some common point of using some tools for merging data from different satellites and topography and also textures and so on. So there could be also a nice exchange with the Earth scientists on that. And at some stage also we could find some analog of some of the subglacial rivers on Earth. So maybe when we go to Iceland, which we discuss tomorrow, we will look at some possible also field work. So, okay, so now on this topic on Moon and Mars data, I have presented before some of the Smart One images. We have some Mars Express images. We have a database at ESA. It's called Planetary Science Archive, which is fully open. You can register, and also NASA has developed a system it's called Planetary Data System, PDS, and they have developed also a number of tools, Moon Trek, Mars Trek, where you can really get some of this data and play with them, so all of us. And I want also to advertise the fact that ESA has launched also a new platform. They call it ESA Data Lab, where you can, for instance, have some software and also share software that you develop to analyze data that are on either archives, Earth data or planetary data. And so that will be something that will be very much of interest to our community. Good, so this was for Moon and Mars data. So the next step is now to go to the Moon and Mars. And this is what we have done last October in the frame of the MPOL campaign. MPOL is for EarthMoonMars Poland. And so I would like to invite the various MPOL team to make their presentation and show their first results. So we have Roxana, Roberto, they were the commander of the MPOL campaign. And we have Agata, who is our host at the Analog Astronaut Training Center in Poland. So in what order do you want to do it?
Don't you have Jourdain before?
Yeah.
Yes, very good. Oh, I need another anchor for this. The floor is yours.
Hello, everyone. I'm Jordan, a fourth year student studying geology in St. Andrews. I'm doing my presentation on the multispectral analysis and geological context of the lunar landing sites. So this is using M3 data gathered on the Chandrayaan-1 mission to basically take these lunar landing sites and then create the mineral maps from them. So the main aims of this project basically to create the maps for the Chang'e 3 and 4 landing sites, and then relate these to the National Research Council goals. So that's goal 2 and 4. So the main reason we want to do this is to be able to comment on the suitability of these landing sites, and then also, can we understand the lunar mantle from these maps? So why do we actually observe the minerals present? So the main reason is the National Research Council's goals. They stated in goal 2 that the structure and composition of the lunar mantle interior provide insight into the evolution of differentiated planets. This basically means from these maps, can we understand the lunar mantle? So the South Pole Atachan Basin is a basin present on the far side of the moon. It's about 2,500 kilometers in diameter, and it's one of the largest in the solar system. So basically here, we want to know if the craters have exposed lower mantle material. And can we understand the suitability from these landing sites? So the first stage of my project is to locate data, which I use Quick Maps for. Quick Maps is a web service which allows you to select various overlays on the moon. So once I've selected the area that I want to gather, I can gather it from the NASA PDS database service. And you can gather these multispectral data sets, which have 85 spectral bands, so they're very large data sets. So I use these overlays in Quick Map to basically get an understanding of the geology before I create my more detailed high resolution maps. So then once I have this data, then I need to analyze it. So we need to constrain these data sets because they come in huge formats. So we need to basically pick an area of the map that we want to understand and explore, and then cut the data sets in order to plot them onto a base map. And then we need to actually undertake the multispectral analysis. So to do this, we get an algorithm for every pixel on a map, and we can change the reflectance values to understand minerals present. So once we've done this, we need to remove noise from this image. So we can do this in 2 ways. Firstly, a flood fill algorithm basically goes through the entire map, and we can use it to get the pixel sizes for these reflectance values, and then delete values that are too small, which basically correspond to noise. This can also be done using a smoothness filter. And then once we've done all this, we can mask out these values to create a nice looking map and overlay it onto a base map. So here you can see this blue map is the map supplied to us in like a band from the PDS database. So if we apply an algorithm to this, we can get something looking like this. This is just a basic FEO map for the moon. And then we can extract values that we want and create an overlay to create something like this. This basically tells us where the iron-rich areas are. So the first area that I undertook was Chang'e 3. Chang'e 3 is a bit basic in its geology compared to Chang'e 4, so it was a very good place to test my analysis on. So Chang'e 3 is on the Mare Imbrium. Mare Imbrium is an area on the near side of the moon. So the Chang'e 3 mission wanted to gain insight by using ground penetrating radars. So now moving on to the Chang'e 4 site. This is a lot more complicated. It was launched on the 3rd January in 2019. As you can see, this is images taken. here and here. And it landed on the von Karman crater. So the von Karman crater is located in the South Pole Atacama Basin. And this is very important because it could provide information to the mantle, and then we could add to the lunar evolutionary story. So the main aims of this lander was to measure the lunar composition and the temperature. We can use these composition values to correspond with our multispectral maps to kind of check our results. And it's a very good moon mantle analog. As you can see here, this is what QuickMap gives us if we select an area. So you can see the crater in blue where the Chang'e 4 landed. So for the first map, I will select this entire crater to try and understand the geology. One of the most interesting parts about the crater is right here in the center. This could be a region of neuritic material, which would indicate to us mantle processes or lower crust processes, which is a very important thing to understand. So progression. So the next steps in order for me to create these maps, I would like first to create a calcium pyroxene map for this Chang'e 4 landing site. This map would be used to identify this neuritic zone in the crater. Furthermore, there are craters to the southeast of the Chang'e 4 landing site, which are very, very crucial in understanding the lunar mantle, because from other studies, we can confirm that neuritic rocks do exist here. And we can also apply this work to the Lunar 25 and the 27 landing site. Thank you very much.
Thanks, Jordan. Okay, so clearly, yes, we are, thanks to you, we are already landing on the moon with beautiful data from orbit that can be compared with the in-situ data. And yeah, and we want to also explore possible future landing sites.
Yeah.
Also, you know that in 3 days, we will have a new mission that is being launched to the moon. That's Chang'e 5. So the Chinese are almost ready. They are on the launch pad for this robotic mission, and it will go even to return a sample from the moon, from an area we have not explored. So that's a lot is happening on the moon side. And also in the context of preparing for the moon village, we want to have a detailed studies also of the midterm landing sites. So that's a work where Daniel Dan is going to join us at some stage from January, and he will work also on even more prospective landing site that will be of interest during the human exploration phase. Okay, so any question on Moon and Mars data analysis? You see a great progress. We have also to put our act together because it was the preparation for instance, for ExoMars. There will be also some mapping work which will be needed to analyze the context of those sites. And I know also there are a number of PhD positions that are advertised in these areas in some of the ExoMars teams. So if some of you are interested, I can put you in contact. So now we go ourselves to the moon. And we start with Agata Kolodziejczyk from the Analog Astronaut Training Center in Poland.
So I want to briefly mount you in the environment where we spent 2 weeks all together, Analog Astronauts, Mission Control Center team, Bernard and me. So these are our crews. You can see on the right, very happy because this was the beginning of their mission. And 2 crews were composed of a big team from Toulouse and Paris from France. And these were IPSA students with the teacher, Roxana. And then we had 3 outsider people. We had Roberto from Italy, we had Amanda from Canada, and we had Christian from Poland. So these were all people participating in MPOL 1 and MPOL 2, and they were running their mission, the simulation of the lunar mission in the habitat. Here you had the main plan of the EarthMoonMars habitat. It was very confined. It was 58 square meters. You can see here the modules: bedroom module, laboratory, kitchen, geolab, gym, and of course, sanitary module, bathroom, and shower and toilet. What was interesting also here in the habitat, we had plenty of sensors, and this is the general map of different types of sensors. So we had multi-sensors, we had specific sensors measuring specific parameters, and we had 3 cameras. So this was habitat, and MCC, Mission Control Center, was in the wooden house. Here you see Mission Control Center crew. This was the site where we were located. And this was how the office of the Mission Control Center. So it was nothing very special, but laptops and brains, this was very special. And of course, beside running the simulation, we had different types of trainings during the time in Poland. Here you see happy people training outside on the Queen Jadwiga pathway. We also had some small EVA, some small photo sessions with Bernard. So thank you very much for being with us in Poland. And beside the mission simulations, we had, of course, our EurMoonMars workshop in Poland, which was also very nicely organized and performed. So coming back to the habitat, analog astronauts, they will speak more about experiments they did during the mission. So I will focus mostly on materials and methods that we used to organize this kind of mission. So our background, our handbook was mission manual, which had 54 pages in total, and it was a general information how to perform the mission. So it was something what kept us that all we understood what we are doing. This was our map, how we should go and where we should go. And with this map, we had also procedures, we had instructions, and there was also possibility to override this manual. So analog astronauts had possibility to override their own experiments, their own procedures. Besides our handbook for the mission, EMPOL 1, EMPOL 2 mission, we had, of course, equipment which was needed to perform properly the simulation, and we had a 3D printer sponsored by Zortrax. We had a special water with 9.4 pH. It was the basic Aquavia water from Romania, also sponsored. So thank you, sponsors, for all this huge support. Then we had aquaponic system prepared by the previous crew. It was a Destiny crew who made the skeleton of the aquaponic system, and based on this skeleton, EMPOL 1 and EMPOL 2 crews, they started to design a functional aquaponic system. Then we had random positioning machines to simulate microgravity and lunar gravity. And we had some regolith samples like a lunar simulant and Martian simulant. Of course, we had materials for the laboratory work like agar, petri dishes, several chemicals, and what I already mentioned, multiple sensors. Here you can see how we observed and analyzed the habitat. On the app of the slide, you see the application. This was on smartphone. There is a blue arrow showing the Habitat OS. So Habitat Operational System or Operation System. And when you enter this icon, you could see again 3 types of icons, which you could use to see, to observe and monitor what happens in the habitat and outside. And first we had a home coach, like a function application, which was used for monitoring alarms and siren activation. So when there was some problem, we could alarm the crew by using siren. And we had 3 types of sirens, like a standard siren, and then barking dog and crying baby. So it was interesting. Then we had Netatmo, a special application for monitoring weather and external data. And then we had a security, habitat, environmental data. And here on the down of this slide, the lower part of this slide, you can see how this application looked like. So we obtained from each separate module plenty of parameters. This was actual parameters. They were made every 5 minutes. This was the resolution of measurements. And for example, here you see the gym air quality, and that everything is fine. We also see the temperature, the humidity, CO2 levels, and noise in decibels. So you see the main information, and of course we could see this information in graphs. We could see statistics, and we could see averages. For example, on the screens, on the plots, which you can see in the middle, we see the temperature and humidity in the bedroom of analog astronauts, and you can see some parameters here from 15th of October until the end of the mission. I will look closer in a moment for some more interesting parameters. Also on the right up the plot, you can see how the noise was measured, and that there are some fluctuations of the noise. So there is not a plateau state, absolutely not. And here you see more detailed data in the plot on the left right corner, where you can see higher resolution of data. And on this slide, I will show you some very interesting and very nicely performed episode. One group was dancing in the galley of the habitat, and in a moment, CO2 levels rised, and we immediately were alarmed about the levels of CO2. You can see on this right plot, the yellow one, the table, sorry, not a plot. And you can see that the CO2 levels are relatively high. So we made like this. I got the alarm from my application. I told MCC to alarm analog astronauts in the habitat. They alarmed astronauts, and immediately analog astronauts, they switched on the air conditioning machine. Why they didn't have switched on air conditioning machine during the dancing? It was because they simply wanted to have higher temperature. And of course, air conditioning was also cooling down the habitat. So in total, I must tell you that the whole reaction to sort of repair this situation, to get to the nominal values, all this time with communication process and with procedure took 2 minutes. So it was very good operation, and I'm very proud of both Mission Control Center and Analog Astronauts crew. You can see also here on the lower graphs this air quality parameter, CO2 levels, and you can see the difference between MPOL 1 and MPOL 2 over the time. So that's kind of interesting, I must say. And you have a gym and bedroom. So there are different values in the gym and different values in the bedroom. Why we need this data? We need this data because we are building a special application like a board computer to operate the mission, to control the mission. And this is based on artificial intelligence. We had already one lecture about applying artificial intelligence and helping us, humans. Matt, my partner, he is writing Habitat's operational system. And we did not use it during MPOL 1 and MPOL 2 missions, but all this data coming from MPOL 1 and MPOL 2, they are now analyzed, and we are now trying to optimize analysis of some like to say, dangerous situations, and how to alarm and how to perform all signaling, all communication very effective in order to feel safe in the habitat. And the final thing which I wanted to say now is mission evaluation. Maybe you are interested how we evaluate this kind of missions. And of course, we have two perspectives. We have analog astronaut perspective and we have a mission control center perspective. So we ask both crews about the mission, how they evaluate it. And we also evaluate some standard parameters like water use, sport quality, and quantity, because some people can run, you know, just, okay, now I have scheduled my time for running, I will run. But in fact, it is not really running I want to train, but it is okay, I have to fulfill all this hour with the sports while I'm doing this, but without increasing the heart rate, without energy, power, and so on. So we are evaluating also hard amount of motivation into the tasks. Then we had this kind of parameter like energy consumption, diet. So how analog astronauts were exactly with the diet manual, because for each day there was recipe for breakfast, for lunch, and for the dinner. So we were analyzing how exact analog astronauts were performing these diet indications, diet procedures. Then we had sleep quality measurements, circadian rhythm measurements, and waste quantity. We quantified the wastes out of the mission. And there was another evaluation factor, which was tasks. And we had tasks which crew started during the mission, tasks which crew completed during the mission, and tasks which were terminated because there was the mission end and they must be terminated. They were not completed, but they had to be terminated. And of course, in this chapter, we also analyzed emotions. And then we had emergency protocols, how analog astronauts performed the emergency protocol. So first, Mission Control Center sent emergency protocol to analog astronauts, and then they observed if analog astronauts were really doing step by step the procedure, the emergency protocol. So it was measuring of accuracy. Then, of course, we measured teamwork versus individual work, schedule, role and responsibilities, communication. I mentioned it in red because this was actually the largest problem during EMPL 1 and EMPL 2. But this is normal. So there is nothing special here. Communication simply is very crucial thing in such analog missions, in any missions, I think. And of course, contact with reality and cleaning, then outreach, new creative ideas, documentation, failed issues, and again on the red, number of publications. This is what we are really interested in. We want to run the mission which give a real result, like publication for us is very nice result. And of course, we compute the overall costs and levels of satisfaction. So these are examples of mission evaluation. Yeah, here you can see. Before I will start, I want to say that during the EMPL 1, we had 5 people. During EMPL 2, 4 people, because Amanda couldn't stay for a longer time. So she was analog astronaut only during 1 day. So we didn't have equal teams. So please don't try to compare the results. This is a different number. So water drinking for EMPL 1 was 61.6 liters. For EMPL 2, 49.85 liters. And you can see different kinds of parameters, like treadmill was not favorized. All analog astronauts preferred biking. And you see here the values. So during so they didn't like to run, but they like to bike. Also, using wet wipes was different. For EMPL 1, it was 24. For EMPL 1, 20, which is very nice result comparing to other missions that we performed in the habitat, it is very nice result. And then tasks started. Again, for EMPOL 1, we cannot really compare EMPOL 1 with EMPOL 2 because this was like a continuous project. So EMPOL 1 crew was supposed to start several experiments, and EMPOL 2 was supposed to finish, to complete some experiments. So here we see that tasks started were 14, 15, but tasks completed were different. For EMPOL 1, 5, for EMPOL 2, 12. What is good? And regarding contact with reality, EMPOL 1 was much more isolated. They tried not to use internet, not to use communicators. So they really tried to be on the moon at this moment of their lives, which was very nice. And there were some extra initiatives. For EMPOL 1, it was dancing. And MCC EMPOL 1, they did a special new experiments. For example, Amanda made MTT tests, and these were very nice. I hope she will speak about them. And then we finally had the most educational experience. So we asked astronauts what they took out of this project, and they said that they really learned a lot about human factors, group dynamics, feelings, managing teams, how to do the schedule. So some astronauts, they said that when you have schedule, you are much more effective during the day. And they said that they will try to make schedules for themselves now because it is really working and efficient. And for EMPOL, this is the final, the final slides. For EMPOL, next EMPOL missions in 2021, we will get some new additional features. And the main feature which we are proud of will be EVAs. So now we didn't have any extravehicular activities. We didn't have proper equipment and nice terrain, but we are collaborating with Dr. Cameron Smith from Department of Anthropology in United States, and he's just finishing making pressurized 2 wonderful suits, EVA suits. They are very professional. We can even fly with them to the stratosphere. So this will be very professional equipment that we will have in the next year. And this is the base. Now we have, just today, we finished the roof of the future base. I couldn't load the photo of inside, but we have very interesting things inside. We have special training equipment, and I hope you will really like it. So this is now a big mess, but we hope we will be ready in the next year. Thank you very much for your attention. And yeah, this is...
Thank you very much. Yes, looking forward, and thanks for your support. Bravo.
Thank you.
So now let's have the crew team. So we start with the commander of EMPOL 1 and the team, Roxana.
Yes, hello everyone, and welcome to our first EMPOL mission. So as Agata just presented it, we are the mission that took place between the 16th and the 22nd of October. Allow me to present you our crew: Joe Podolski, Christian Komenda, Roxana Perian, so myself, Emma Fogmaillet, and Michael Klein. So it's the order that you can see them, us on the screen. Even if you expect me to start, I'm gonna give the floor to my my vice commander, Christian Komenda, who's gonna present his work during our mission. Christian, the floor is yours.
Hello, I'm Christian Komenda, and I'm biochemist. Also, I'm fourth-year bioinformatics student at Jagiellonian University. I took part in EMPOL 1 mission. I was vice commander. My duties were aimed to help the commander and check that all tasks are fully operational. Also, I was in charge of my own bioreactor experiment, which I'm going to tell you at this moment. Okay, so in confined and small spaces, the increased amount of CO2 level generates a potential risk for the crew. Constructing and developing sustainable life support systems are crucial for future space flights and also in long-term deep space exploration. Microalgae consortia can help us to create life support systems, like more sustainable. They are able to reduce CO2 level and also can generate a potential oxygen for the crew. And most of the advantages of that microalgae consortia are cheap price, resistant to harsh conditions such as shaking and a lot of radiation, and they can also reduce efficiency CO2 level. And as you see on the screen, we can see that's real data from my experiment for 3 hours of time duration experiment. We can see a lot of increased CO2 level in our habitat. Also, experiment was started in 3 different algae microconsortia. Each consortia had 3 different types of algae, Arthrospira plantitia, Chlorella, and Cynecocystis. I don't know, I cannot move. Okay, it's okay. On the screen, we can see in the middle 3 different types of microconsortia that they were used. All of them were mixed with different concentration to check the most sustainable microconsortia flask. Also, we can see a photo of microscope photo of Cynecocystis. That's the best microalgae we had inside the flasks. And how the experiment was performed. Firstly, we used, I built it and created box, hermetic box containing CO2 meter, 3 different columns containing containing microalgae, and also all the parameters with like lux meter to measure the amount of light inside. The previous part of the mechanism was showed on the left, and also I was helping, I was using the experiment with RPM machine. That's the special rotor machine that can create artificial gravity on plants, on every algae we can have. So we can arrange the artificial gravity of the moon inside the habitat, so we can see and we can predict how can algae can work outside our gravity and outside our planet. And moving to early results I got from my experiment, I saw that CO2 difference in that lunar gravity is more efficient for reducing CO2 level by microalgae. And we can see on this graph on the left, the difference and the efficiency of reducing CO2 level are much lower on Earth gravity than on lunar gravity. So that's the interesting point. I'm going to check and I'm going to examine that, because this could help us removing CO2 level inside the habitats on the moon. Also, we saw the basic data like CO2 reduction is more efficient during the daytime rather than the night. Also, another work is in progress. So if I will have any data, more data from our results, I will present you soon. Thank you for everything, and I'm giving the control to Theo.
My name is Theo Polowski. I'm an IPSA student at Toulouse in 3rd year. So this is a school where we learn engineering and aeronautics and aerospace. So I've been invited to Poland as an analog astronaut as part of the EMM Pole mission. I was part of the EMM Pole 1 mission then. And my first task was to design some mission patches. So to do that, I inspire myself with the classic. Okay, never mind, we don't see them. Those are the well-known Apollo badges, and I also inspire myself with the space shuttle badges. So as you can see, I did a lot of tests because I wanted us to have the best mission badges possible, and because for me it really represents what we are and our mission. So the two winning badges are those two. I don't know if you can see them. So this is the mission control badge, mission control badges, control center badge, and this one is for the habitat. So can I pass the, okay. I was also the communication officer of the mission. I was responsible of taking pictures and videos of the crew while they were doing their activities, and then send those pictures to the mission control center. As a communication officer, I also had to communicate with the mission control center about our daily experiments and lives. One of my other tasks were to be responsible of a brand new 3D printer. So I had to set it up, and to do that, I had the help of my colleague and friend, Mr. Michael Klein. I was also responsible of the 3D designing of any part of the mission. And also the 3D printing. So I could help, for instance, my crewmates if they wanted to do a project which need 3D printing parts. For instance, Emma Fangmaillet, for the aquaponics system, wanted some cups to hold plants. And she gave me basically the measure and what she wanted, and I designed on Katia, which is a 3D modelizing software, so the 3D model of the cups, and then print those down in a few hours. So one of my other main goal on this mission was to work on a concept that I imagined with my friend and co-worker, Mr. Quentin Gouault, which is in the EMM Pole 2 mission. So this is called the micro launcher. So the concept behind the name is that it is a sort of 3D printable rocket, so composed of 3 different parts. So a tank to hold the compressed air, a thruster to propel the ship, and a sort of lander to bring back samples. So the goal of this thing is to be 3D printable, for instance, on a lunar base, and really easy to assemble. The goal of it is to send some lunar regolith samples or other celestial body samples in orbit or back to Earth. So what I did in my first week mission was to work on an analysis of the pressure of the tank. So the tank has to hold 100 bars, which is really huge for a 3D printed part. So as you can see, to handle the pressure, this is really thick, a thick tank, yes. So here's the 3D printed part. And the sort of green balloon you see on the screen right now is an analysis of the deformation amplified when the tank is under 100 bars. So also the sort of little thing you see on the top is a solenoid valve, which has the purpose of letting or cutting the airflow. To finish my small speech, I would say that this is a really great experience for me. This was really gorgeous. I really enjoy it. So I'm really passionate about space, and for me it was like a dream coming true. I think I learned lots of things during my mission. I learned about how to communicate in an efficient way, and also how to 3D print, which is something I guess I want to do maybe after in my daily life in future. And also, I would like to thank a lot all my crewmates for being just so awesome during this mission and for represent now a sort of small family.
So hello everyone, my name is Emma Fogmaye. I am 21 years old and I am a fourth year IPSAT student. I am part of the EMMPO1 mission. So during my stay in the habitat, I was the astrobiologist. I was taking care of the aquaponic and the hydroponic experiments. And I was also doing space weather reports. And then during my stay in the MCC, I was the records officer. I helped to improve the aquaponic system. And I also helped in doing emergency protocols and experimental protocols. So this is what the aquaponic system looked like when we entered the base. So to explain very, very quickly, the fishes in the tank produce ammonia, and that is turned into nitrates by bacteria. And then the pump pumps the water, it goes up, and then through an organic filter, it waters the plants, and then it goes back down in the fish tank. So this could be useful to grow fresh food on the moon, for example. So during my stay in the habitats, here are a few tasks that I performed. So I isolated the aquaponic system to prevent germs from the habitats from contaminating the plants, especially because the aquaponic system was close to the gym. I also installed lights in the system because, of course, with the isolation, the plants had no lights. I also fixed the water flow, sorry. And I had two main issues during my stay in the habitats. The first one was a water issue. Basically, to explain very briefly, the nitrates rates were way too high in the water. And this is toxic for both the fish and the plants. So with the help of MCC, we decided to change the water from the tank, and EMMPO to continue to do that when they were in the base in the second week. My second problem was that there were algae at the bottom of the tank, and we figured that this was because there was too much light entering the tank. So we added duct tape to the fish tank to prevent too much light from entering it. I also built a very simple hydroponic system by using plastic bottles and 3D printed cups that Theo and I designed. So this could be useful as well in a lunar base because you can grow fresh food without any soil. I use different types of cups, like baskets that you can see, and different types of water. And EMMPO to continue this experiment in the second week, and I waited for the results to see how the different parameters influenced the plant's growth. My last task was doing the space weather reports. So as you may know, on the moon, there's no atmosphere and there is no magnetic field. So there is nothing to deflect the radiation, the solar radiations. So if you're an astronaut on the moon and you want to go out, you have to check that. You have to check the space weather because otherwise it's dangerous for you. So I would do space weather reports to predict whether or not it would have been safe for astronauts to go on the moon. So to do that, I would monitor the solar flares levels and also the sunspots by looking at photographs from H-alpha telescopes. During the second week, I was in MCC. So I continued to help with the aquaponic system. One of the tasks was to improve the biofilter. This is because the nitrite rates were still very high. So we wanted to increase the nesting surface for bacteria to settle in and to lower these rates down. So in MCC with Theo, we designed these little wheels, and EMMPOL2 3D printed them in the habitat and put them in the fish tank. And we hope that this will help to reduce the levels of nitrates. I also received some results from the hydroponic system. So here you can see some photos on of the last day in the habitats. And I received some data, for example, the pH and the water hardness. And I'm going to see how the different parameters influenced the growth of the plants. This is an example of what we would do in MCC for the analog astronauts in the base. So we wrote an emergency procedure. This was about a toxic spill. This is something that can happen, for example, on the ISS. So what we would do is we would write these type of procedures and then send them to the analog astronauts that were in the base at that time. And we would ask them to do some reports on the situation and on what happens. So thank you everyone for listening to me, and I'm gonna give the control to Michael.
So hello everyone, my name is Michael Klein. I'm a fourth year student at IPSA. I'm specialized in mechatronic. During the EMPO1 mission, I was a data officer. It was a strict and important role, so I must prepare all the data table, collect all the data within the crew that concerns the reaction time, circadian rhythm, Sudoku tests, sport, and many other activities. As a data officer, we must make the data as clear as possible for the mission control center. So you must be precise in your work, and diligence, precision are the keyword of this role. So I was proud to be within this group. I also conducted my own experiment named NAVOT, so that is not a waste of time. I think waste management is an essential domain to guarantee the success of future humanitarian mission on Mars, on the Moon, and we must try to reduce and make reusable the waste carried on board. Before the experiment, I contacted a company named Zeapack, which gives me a wet towel and gloves or straws and other items, other compostable items, in order to guarantee the success of the experiment. Inside the base, there were the three main items that were used by the crew each day: the gloves, the wet towel, and the garbage bag. We conducted various simulations during the base, and we noticed an increasing of almost by 2. Yes. After this, the main point was to create a compost rich in nutrients with this compostable waste. So I started the experiment, and after Julian continued. So we separate into 2 jars some samples of wet towel and gloves, and study their transformation into compost. So we try to conduct the Berkeley method to create a compost. The Berkeley method is a way to do the compost by put the samples in the heating system to make it more warm, and yes. So each day we must take the parameters like the pH, temperature, and humidity to see if we are in the good way to create the compost or not. However, this part of the experiment shows no concrete result with the parameters, and I think it would be more suitable to have more time to prepare an experiment like this. I will work on this to improve the project, and will conduct further researches in other domains that can be useful. So I will identify non-compostable items and we'll 3D print. The idea is to 3D print them and get the offcut back to reuse it. During the second week, I was also the data officer in the MCC. So it's quite the same role as in the first week. And it's really important to check and verify all the data, especially because in the Excel table that we have in between us and the crew inside the base, when they put a comma in a number, the Excel table doesn't understand and doesn't consider this as a number, and we must check all the mistakes like this and yes, check it. I was also the schedule officer during this second week. So the task is to prepare the schedule for the astronaut analog. We must consider the tasks that must be performed during the day, must take into account the feeling of the crew, consider the crew needs in order to make them more comfortable inside the base. It was really an interesting and enriching experience with all the EMPOL crew. I really thank the company ZerPack, but also EarthMoonMars, AETC, and EMPOL in general. And special thanks to Roxana, Christian, Theo, and Emma, which are my friends and my family too. It was a wonderful experience and with wonderful people, so thank you, and I let Roxana continue this presentation. Thank you.
As you already heard, my name is Roxana Perrier. I'm from Toulouse. I'm a doctor in physical chemistry. My daily job is a space science and physics teacher. And during EMPOL 1, I was the mission commander. What was to be a mission commander during COVID situation? The first thing was respecting the restriction related to this special sanitary conditions. But you need to know that if at first we were very careful, after a day where you check your temperature every 2 hours, when you share the same very closed system, we started to perform our day-to-day tasks with no masks on. During the science tasks inside the habitat, I had the chance to help my vice commander for his biocontamination experiment, and prepared the petri dishes with nutrient agar, and of course help him take samples from all the surfaces that analog astronauts will touch mostly. So you have to, as Christian mentioned it, while traveling to space, inside the module, space module, but also inside the space habitats on Mars, on the moon, or somewhere else in the solar system, the human being will influence his own environment. So this type of experiments are really crucial during a manned mission. So besides this, Agatha mentioned it earlier, we had the chance to have a 9.4 pH natural water. So we experimented it, as Emma mentioned it earlier, on plants, but also on ourselves. Analog astronauts, we had a special diet in order to see what is the influence of this high pH water on the human body. We will have, of course, the results. We're only 1 month after, we not having yet the results. The data are treated and the samples will be analyzed further. As a mission commander, I had to make sure that all the schedule that the Mission Control Center was sending us every day was respected for all the activities, and even for sports, because I don't know if you can see it from the pictures, but the sports room was really small. So we, as Agatha mentioned it earlier, the CO2 levels were were going up very fast. So we had to make sure that we would be only one in a sports, in a gym, or only one in small areas. As a commander, I had to make sure that all the team sticks together. So mainly the most of the day we were focusing on our individual tasks, but also as you see it in the picture, while cooking breakfast, lunch, or supper or dinner, we will be all together. So it would be a very nice and comfortable moments to share for us, preparing dinner. But the team building would be was continuing even outside the habitat after 1 week inside, while gathering with our MCC crew, so our mission control crew. We were happy to see them, so we were excited to spend 1 day with them before them getting inside the habitat. But once outside, we did not forget that we were still analog astronauts, and we are all keen to go to space. So we continued on training to keep in our good shape, but also working, because we, as you see, continued on training as future astronauts. So we went to the observatory, checked on the moon and on Mars. Observations are really important for our future missions. We had drone piloting training. Drones are very important also for bringing samples or bringing back samples from the habitat. Working as MCC, Mission Control Center for EMPL-2, for myself was being a flight director, so making sure that all the tasks were daily done day by day by our crew. As you see here, we had our communication officer, our data officer, our astrobiologist, and a medical officer, that was Emma, during the second week. So we were taking care of our crew that was inside the habitat, that was EMPL-2. I would like to give a big high up and a big thanks to Professor Bernard Foing and Dr. Agata Kolodjechik. I'm sorry, Agata, if I pronounce it badly. I thank you for this huge opportunity that you gave us to be able to train in your habitat, and not only to visit Poland. We as a crew would like to thank our Mission Control Center, all the remote support from all over the world, especially the one from France and Korea. A special thought to Kevin and Michael, who should have been a part of the EMPL-1 mission but could not join us because of the COVID situation. And our crew, our dream crew, EMPL-1, as you see, we used our drone training to make beautiful pictures of us. That's the one made by the EMPL-1 crew. So thank you all for your attention, and the floor is yours. If you have any questions, or if not, I'll give the floor to EMPL-2.
Bravo, bravo, EMPL-1. That's great. Okay, let's get the EMPL 2 presentation, and maybe we have a general question on everything, including the. Okay, so Commander Roberto and the team, the floor is yours.
So first of all, hello everyone. I'm Roberto. I'm the commander of EMPL-2. Today I will talk about the mission, how we manage the mission, which is the results of our mission. I will talk about my research about the smart habitat, and then the crew will present their work and their results. So here you can see who we are. We are not robots, we are people. You can see me, Roberto, my vice, which is Julien, Amanda, the medical officer, Hugo, the astrobiologist, and Quentin, which is the communication officer. First of all, which are the main objectives of the mission? So the first one is to investigate the isolation condition of a crew during 1 week. So basically, which are the main physical and psychological reaction, and to understand how we can to reduce this effect and how we can to improve the physical or the psychological status by using, for example, new tools or by improving the habitat design. The second objective is to study the impact of human on the habitat. So to study how to design better and better habitats based on consideration on human action, and to correlate effect, for example, detected by a sensor with human actions. And we can see in a few moments the effect of, for example, human actions and human activities on CO2 level. And the last one is to carry out some experiments. You see something about aquaponics, about hydroponics, and to study some samples. So you can to see in the following minutes something about that in our presentation. So we can, here you can see what we did. So basically we worked both for MCC during the first week to support the EMPL-1 crew, and to participate as a crew member also in Habitat during the week 2. It was not during the first week. We was not every time in our habitat. We performed a lot of activities. Here you can see our EVA activity expedition on Mars. It was very nice. We really enjoyed this moment. It was very nice to understand how to communicate with external people and how we can to also perform activities during a space expedition. So it was very also interesting, not only enjoying it, but also interesting. And another, we can say, journey we performed during our MCC moment was the astronomical observatory visit, and we visited the astronomical observatory, and also we took some driving session with a tractor. And also we performed some observation of moon, for example. You can see on the left, and also a very funny moment. It was during the first day. It was the team building during which our car remained locked on the mud. We tried to find a solution to unlock it. And now you can see the habitat experience. You can see some activities, so outreach activities, online workshop, daily test, of course, work session and daily session and sports session. And here are some results. So now we will talk about the habitat smart sensor and results. But also we will talk about the 3D printer and two aquaponics system. Now, first member is me. I'm Roberto Andolina, a master student at Politecnico di Torino, Italy, and also I'm EarthMoonMars intern for 1 year, during which I will develop my thesis focused on smart habitat and habitat design, both on a mission overview and on a design of systems. And why I'm doing that? Because I'm a very visionary person who loves all visionary activities, all visionary projects. So I would like to see people on Moon Mars, and I would like to contribute to see that. My work could be resumed in this slide. I was, first of all, the commander. So I don't want to talk more about that, because I think that Roxana explained very, very well which are the tasks of a commander. So to define the roles and to check that is carried out to check the schedule, basically, to take the most important decision, to keep high the motivation, and of course to solve problems between crew members if it's necessary. The second work, it was as a system engineer. You can see the function, and also you can see that in this case I put some arrow. That is why you can see the flow of the function of the activity from the investigation to the identification of the solution and corrective actions, by passing, for example, to analysis and other tests. And the last one role, it was as an outreach officer. So I helped Sabrina to gather all photos, to write posts for social, to organize workshop, and because it's very important in this moment to talk about our experience, our project, because it's the moment when we have to educate new people for the job of future, to educate for research and space stuff. Here you can see an overview about how I performed the role of system engineering. So you can see which were the main questions of the research, and also you can see how this question could be answered by using the function that I defined in the previous slide. That is, in fact, you can see that in this case, the yellow boxes, which are the function, it was the same of this one, so the same of the central column. Because of course, the only way to gather the results and the objective of the research is to use this scientific process. Similar process, it was also used for a smart sensor. In this case, the results was focused on air quality and CO2 level, and the purpose is to link the CO2 level with the human aspect. And here you can see the main questions, which was very useful to carry out the research. About electrical power, some results. Now you can see in the low part of the slide the two plots of power consumption during ampule 1 and ampule 2. And you can see that roughly they can be approximated with a line. That's mean that the power consumption remained the same during every day. So it was constant. It was roughly 60 kilowatt per hour, roughly. And same for ampule 2. It was roughly the same. In the upper part, you can see the operative module, which we defined, and the analysis of the device. Why that? Because as you can see, the first step is to analyze which are the main device that require power, and the second to define the operative modes for the research. Operative modes means the moment when roughly the power consumption is constant because the activity performed are always the same. About our quality, you can see 3 plots. The first one is about to study how the CO2 level change during the day. It is the average values for each hour, you can see. And as Agatha said, we gather this data for every 5 minutes. And you can see some interesting things. For example, the level remained constant during the night. So, for example, between 2 a.m. and 7 a.m., basically, you can see some peaks, especially in the morning and in the afternoon. And then you can see some very interesting path. Other question was about which module was the most dangerous, we can say, and you can find that, for example, the bedroom and the galley was the more containing a CO2 module, you can say. And instead, the laboratories and the gym, it was not very high. You can see in gray and yellow. And finally, you can see also the path during the day. Here you can see other results if you want to see something. Okay. And the last one, it was about the communication. So it was the last system, very interesting because it's a cross between the human factors and the engineering. So the main purpose is to design a communication system which take into account both the human factors and the engineering one. And the main purpose is to choose, for example, protocols to get the communication more and more efficient, or to, for example, use okay, or for example, to size the hardware so that we can reduce the data volume, which is very important data for parameters for the system design. And also you can see in this case the questions and the function. You can see.
Excuse me, Roberto. So we actually have to make just a pause now because we have a special guest that Rogers, that is the founder of the International Moon-Based Alliance. He was just with us for some time and he just has to leave soon. So I want to give the floor for a few minutes to describe what is the status of the base in Hawaii, and then we'll come back right to you.
Yeah, I'm on my way, so I'm going to be talking from the car.
Oh, okay. As usual, the typical Hank, yes. But
just quickly about high seas, we are in the process. We've had 4 missions, 3 back-to-back right now. So we are running missions in high seas. And on the IMA side, we're designing a device which is going to move things away from the rocket that's going to land us 100 tons on the moon in 2024 and build a structure. The basic idea is that, if you land something on the moon and you have something like a lift that lowers it to the moon's surface, you have to move that stuff somewhere else, because otherwise when the rocket takes off, it'll be destroyed. And so this device, I believe that it's a device that needs to not only be able to move things around, but then use that same device to actually construct things. Structure or habitat construction. Phase 1 is where we have a complete unit like the ISS that's made on Earth and gets transported to the moon in one piece. And phase 2 is where we send up parts, and the parts get constructed into something bigger on the moon. So that phase 2 is the thing. I'm looking forward to starting some kind of a competition between engineering groups, students around the world, to see who can come up with the most interesting phase 2 construction machines. So that's basically where I am right now. Somebody told me that they have a material that's radiation proof, and I don't believe it yet. So
okay, so I think that
2 meters of regolith. Anyway, that's it. That's where I am.
Excellent. So we are looking forward to having a campaign next year. So we had to postpone it, and I see some of astronauts we have trained now. So some of them are eager to come to Hawaii and to have some campaign. Also, some of them are developing some concept for a new habitat design, so that we would like to test here. But why? So we are, well, thanks. So you are back into your pressurized vehicle on your towards your next destination, as usual. But okay, it's self-driving, huh?
Yeah, I'm looking forward to seeing your teams coming to Hawaii and spend time in our habitat.
Yes, so you are looking for. Thank you. That's also okay. Good luck to you. Yeah, okay.
All right.
Okay, goodbye.
Au revoir.
Au revoir. Thanks. Okay, so that was Eric Rogers, one and only. And okay, so you see that he's the founder of the International Moon-Based Alliance, and also of this lab, energy lab that where we stayed in Hawaii, and we have he's very much also looking at solving some also global issues. And so now we are back to Paul, and I think it was good that he could listen to some of your presentation for all the Paul team, and also we see what we can project also in collaboration with for the next campaign. So back to you, Roberto.
Yes, so now here you can see the future work. So the basic idea is to improve this kind of research to maybe prepare new protocols for future mission, to investigate and then to put together the data in order to maybe see the effect of corrective actions on systems and how to improve that in following loops. And that's fine. And here you can see our outreach events with ESA Torino and with Aeroavia Pisa, which was very successful. So thank you very much. And now, Julien, it's your turn.
So, hello everyone, my name is Julien Barin-Codine. I'm a fourth year student at IPSA, just like Michael, Theo, and next Hugo and Quentin. I will be specialized in mechatronics. I have a lot of actual projects which are suspended because of COVID. So the first week it was in the MCC, it was the crew medical officer. I was responsible of collecting the data every day and to ensure every analog astronaut put all the data on the good file. And like Michael said earlier, I had to make sure they didn't use, for example, commas, but dots for the Excel to have some good plots. And in MPOL2, I was the vice commander and responsible of the social distancing experiment. It was an experiment because of COVID to analyze the effects of social distancing on a small habitat, in a restricted and very limited habitat. So every day, analog astronaut had to answer 10 questions, like if they respect social distancing, if they wash their hands before and after starting an experiment, and the effect of social distancing on their work. And as a result, it is impossible to avoid the contamination inside a small habitat without other things than social distancing. So we have to wear masks and to wash everything every time to make sure everything is perfectly clean and to not have infections. Okay, now I pass. So I was the I was the crew medical officer, like I said. So you can see the Google Drive you used for during every EMPOL mission, and every day we had to make sure everything is filled. Like every morning, I checked the sleep reports, and every 2 hours I had to check the circadian rhythm to make sure the astronauts had fully completed their parts. Device commander control. Role, sorry, it is just like the commander control, but thanks to Roberto, I had not to play this role a lot because he was a very, very good commander. So thank you, Roberto. But he had a lot of things to do, like a lot of workshops, and his study were taking in a lot of time. So when he was busy, I had to take the role of the vice commander, like to make sure my partners, the crew completed the sheets to make sure everything and every experiment was okay. I was also helping with the aquaponic. Hugo will tell you later. And just like Emma the first week, I was responsible of the space weather reports. and I was the supervisor of NAWAT. Michael has done the work completely, so every day I just had to check the pH of the sample, the humidity and the temperature, and to add water if the humidity was too low, for example. So the space weather report, Emma told you earlier what it was for. It's for astronauts to make EVA on the moon or on Mars, because there is no protection from the a field on Mars or the moon. So we have to make sure everything is perfect. So I took an example of the solar flares from October 28th. So the value A and B, like you can see on the bottom right, are useless because they are very, very common. But when you start to being on C or more, it can be dangerous for astronauts to go outside. So it is very important to monitor every day all these values of the flares. I also checked the sunspot region and their magnetic classification and the density of proton coming from the sun, because you can have a lot of interference in your communication during real dense solar Bronto waves. And every day I had, just like Emma, to write a report and to confirm or not if astronauts could go outside. Finally, the aquaponic. Hugo will tell you a lot of it because he's an expert. He gave me a simple mission. We had some sample. He analyzed them in the graph you can see with the pH, the iron, and the nitrates. And I wanted to see the effects on these samples on watercress. So the first day I made a watercress sample, like you see on the picture bottom. And we waited until the last day, and we saw that the sample C and F were the best for the watercress to grow because of the concentration in nitrates, but also because of the low concentration of iron. So it was very interesting. It is very useful because if you want to use aquaponic on space, you have to choose the perfect water to bring, because you may not find the perfect water directly on Moon or on Mars. And I think I will let Amanda continue. Thank you for your attention.
All right, so hi, my name is Amanda Spilkin-Schlutzarczyk. I'm completing my master's in physics at Concordia University in Montreal. And I was part of the EMPL-2 Mission Control Center and only had a short stay in the habitat, but still got to feel what it was like. I'm the founder of the Space Health Division back at Concordia University, and both at Concordia and during the EMPL mission, which I was the experimental officer, I focused on human factors and also doing different studying different platforms for either psychological testing or for diagnostic testing. So I'm going to be focusing on the experiment that I was conducting during the EMPL-2 mission. So it was both on the EMPL-1 and EMPL-2 analog astronauts, and I was studying human factors, but specifically in terms of reaction time and memory. So I will just kind of go over quickly what human factors is, because it covers anything from medical to psychological well-being of astronauts. So it covers behavioral skills, organizational skills, situational awareness, how do you react to an emergency, leadership and communication, which is really based on the framework of mission control and analog astronauts. Who leads, who takes care of medical data, who takes care of communication, etc. The importance lies not in necessarily your role, but how do you manage it. And this was really interesting because after doing a lot of research on human factors, I realized that the habitat is a great place to do controlled testing of all of these features. So as you can see, there were many variables that were already recorded, but there were extra things that we didn't even realize that are studied upon the ISS. So just to go over quickly the two things that I was studying, I was looking at mental chronometry, which is the study of reaction time. So very important, just to give you a ballpark figure, every time you're looking at somebody reacting to some kind of stimulus, the average for a healthy human being is 200 milliseconds. And also short-term memory, which is governed by something called Miller's Law, is basically the way your prefrontal cortex is going to be juggling 7 pieces of information, plus or minus 2, for up to 30 seconds. So this is really important for analog astronauts and astronauts alike, just because you need to be able to remember instructions very well and carry them out successfully. So the way that I measured these two variables. So first of all, the memory test consisted of 5 numbers that were dictated to you out loud, and you had to say them, however, in reverse order. This was done 2 times, once at lunch, once at night. And it was a list of 5 numbers and 3 trials each. The reaction time test was a mobile application, which only one device was used for reliability for time. And basically you had a start screen, which was the orange one. You had to tap on it to have your waiting period, which was the red screen. And as soon as it turned green, you had to tap right away. And this measured the amount of milliseconds duration before you actually realize, your brain realizes and connects to your finger in order to tap the screen. And then you would have your measurement. So I looked at the analysis for day versus night trials. Why? Because obviously as analog astronauts, you are working all day. You're getting up at probably 6, 7 a.m., going to bed around 11, maybe 3 in the morning. And this does have a huge impact on your reaction time and your memory. Also, as the number of days went on that you stayed in the habitat, you're breathing in variable quality of air, you're becoming more tired, and this is also affecting your results. So your reaction time tests, so now all the analog astronauts can see them. So as you can see in the chart on the left-hand side, so 7 out of 9 analog astronauts actually had an increased reaction time, meaning that you were slower at night. So this is really interesting because I think we have a highly functional team because all of our analog astronauts have reaction times that are within the 200 millisecond range. Another thing that I noticed is that as the number of days went on, your results also started increasing on average. So for memory tests, this is also interesting. So this had some variability. Here I have 4 analog astronauts. I'm still doing the calculation to make sure that all of the results are correct. But for the EMPL-2 mission in the habitat, we can see over here that in the grand scheme of the results, in each of these cases, it seems that your memory does have a little bit less performance at night. What does this mean? It means that on average, you recalled less numbers correctly at night versus daytime. Now, there is a trend here as well, where what I notice is that as the number of trial within your run went on, so you're going to recall the first line better than the third line, actually. So this is also probably just juggling your short-term memory. It's a little bit harder when you have 15 numbers versus 5. And then finally, why is this important to keep studying? So in August of next year, 2021, I am planning on returning, if everything goes well, to the EMPL, I believe it's 5-6 mission. And since I do work in brain imaging, I do want to study this a little bit more carefully, because though these results are reflecting more behavioral and just simple memory reaction time tests, we know that this translates into sensory signals. So I would like to do more experimentation, which is going to be looking at hemodynamic response, meaning the amount of oxygenated blood delivered to a certain brain region, which is responsible to reaction time and memory. And it's also interesting because on the International Space Station, each astronaut actually has this COS-IR sensor, which they carry with them between modules. So they're actually monitoring the CO2 level around them at all times, which is then kind of used as, I guess, more heightened statistics. So that is, all in all, what I was studying during my mission control time and my time as an analog astronaut, but away from the habitat. So thank you, and I'll pass it on.
My name is Hugo Gastin. I am a fourth year IPSA student. I'm currently in Paris. In the EMPL 2 mission, I was communication officer in the mission control center. And in the habitat, I was the astrobiologist in charge of the aquaponic system. Also, in the Mission Control Center, I designed something that I will present to you just after for the aquaponic system, and I optimized it with content. So the role of the communication officer is to communicate with the crew, to be responsible of all communication, to be the most clear and concise as possible, because all information of the Mission Control Center are going through you and you are passing them. And all the information from the crew in the habitat are going through you, so you have to be very clear, so information are not lost. So this is a transition, yes, from the MCC team to the astronauts in the habitat. So yes, the communication officer is also a little bit a psychologist, because he has to prevent tensions, takes care of the astronauts and to help and to distress and de-escalate conflicts and monitor the crew interactions. It was the hardest part to me because I was a little bit forgetting it, and I think I did some mistakes for the psychology part. Anyway. For the aquaponic system, so I was in charge of designing it. So on the left, you can see the aquaponic system. So the skeleton that was designed by the Destiny team. So in the first part of EMPL, so the EMPL 1 mission, they isolated it and fixed some water issues and the algae issue. And it needed some improvements, so like the possibility to cultivate a large variety of vegetables and fruits, to improve the biofilter because it was not sufficient, and make the hydroponic part easier to use because it has some defaults that made the cultivate of plants nearly impossible because it was overflowing. So on the right, you can see what changes were done. So we suppressed the black things where this was a little pot where the plants were growing. And you can see on the second stage of the aquaponic system, the tower. So this is a tower that we made in the Mission Control Center. This tower is printable, so it can be used in any mission. It is a customizable structure, so it can be the height you want, and it has a very long time of printing. So we wanted it to be customizable, so the team can print as much part as they want in function of the time they have. And it is a vertical agriculture, so it optimizes the available space. So I did it this on a 3D software with thanks to Quentin, because I had not the skills to do it, and he helped me to design it. So this is supposed to be filled with cocoa fiber in the inside, and you put the seeds, and the water is going from the top to the bottom, and it is flowing out of the tower. So it acts as a giant biofilter, and it will, thanks to this tower, in the habitat, they will be able to grow larger vegetables like strawberries. Also, because we removed the little pot, we are able now to cultivate small plants in large quantity. Like in this mission EMPL2, we tried with watercress. We cultivated it. It is very easy to use. And also, this system captures fine solids, so you don't need a real filter that you have to change every time. So this was my main task. I tried to be to sum up a maximum, so it will not be too complicated, and it is quick enough, I think. So if you have some question, you can email me. Thank you. I will pass.
So good evening, everyone. My name is Quentin Gouault. I'm 20 years old. I'm a third-year student at EPSA Toulouse, so Aerospace Engineering School. I'm a member of EMM since July 2020. And in addition to my studies, I worked on several engineering projects, such as an EVA robot assistant. I developed with Roxana Perrier and Théo Podolski. I also worked on a linear habitat with some EMM members. And finally, I've worked on micro-launcher made in Moon. It's the project I used as an experiment in the EMM Pole mission. Yes. So the EMM Pole mission was during 2 weeks. So in the first week, I was in the mission control center. I was the schedule officer. So my work was to, I thought it was easy, but my work was to create the schedule for each members, for each analog astronauts for each days. But I quickly realized that it was more difficult than I thought, because I need to take into account many elements, and I didn't know the proper time for each activities. But the situation became better and better because I had the feedback of astronauts. On the second week, I was in the habitat, so with my EMM2 team and comrades. So I was the communication officer. So my work, as Hugo presented it previously, was to assure the connection between the habitat and the mission control center. It has two interesting aspects for me. The first one is that responsibilities I had, and I really liked it. It was challenging. And the second point I liked is I need to transmit all the information without feelings. And it was quite a psychological problem for me at some moment, but it was an interesting experiment. So I was also the 3D printer, was responsible of the 3D printer. So I've done some maintenance on it, but I also worked on two different projects. So the first one is the Hugo's and Emma's project, the aquaponic system. So I've helped him to model the tower. So he showed you just before, and printed it. So the printing took the half of the mission for only 30 centimeters, and we wanted 1 meter prototype. So we were a little bit disappointed about that, but we managed to create a useful prototype. And the other half of the mission, I could use the 3D printer for my personal experiments with the experiment I do with Theo. Sorry, it's the micro launcher made in Moon. So my experiment was to model a launcher. The concept is simple. We wanted to have a simple architecture and a simple way to prepare the robot, the launcher, without using any combustion, but only compressed air. So we wanted during the 2 weeks to print every parts of the launcher, such as the tank and the junctions. That's what Theo did. And I printed the thruster and the re-entry module. So the re-entry module, I used the same proportions of the American mission Stardust. So the idea is to put the samples in the module, in the re-entry module, to send it back to Earth. And so you can see the modeling on the right side of the screen with a photo of the print part. And on the left, you can see the thruster I printed. So I didn't took the correct dimensions because we didn't have the final trajectory of the launcher, but we could have some expectation of the dimension of the thruster. So I would like to finish by saying that we printed all the parts with the plastic, which is called PLA. But in the future mission, we won't use this plastic because its thermal and plastic properties are not really efficient. So we'd like to test the print, but with all the materials to see how the structure can react. And of course, I would like to thank everyone, Bernard and Roxana, for giving me the chance to be part of this mission. And of course, my friends of EMMPL 2 and EMMPL 1. Thank you very much for your attention.
Thank you. So that is it for MPL 2. Yeah?
Yeah.
Yeah, so congratulations to the MPL 1 and 2. Then let's talk about the future. And actually, I would like to invite Michael, Professor Meltemate, who was due to be joining the MPL campaign, but is now planning to go at the next one. So, Michael? Yeah.
Good. Okay. So this is the research I was planning, and I'll just go through it very quickly. A lot of you have already seen it, but I had a new idea, and I'm just pursuing that. So this is about robots as crew members, and the initial idea of crew composition was to fulfill a specific purpose, right? You can see that perfectly illustrated in this image. This is exploration, going forward to the future, and as you can see, there's women in the back, and that is because during the first space missions, it was a crew that looked like this: old or middle-aged white guys who were mostly military or all military. And then people expected crew composition to radically change mission types, and they sort of did, but not too much. Right, when Sally Ride first flew on the space shuttle, there was all these ideas how that would totally change space missions, but it did not really change it that much. It was just some adaptation, and it was just some rethinking of social roles. It was human with that. And the question for me, what would change if we include non-humans into crews and not only use non-human entities as subscripts? That's the Viking lander, goes where no one has gone before and well with the technology time. So this is obviously Utah, humans go there, but I'm talking Mars. And other agencies working on robots to substitute humans. That's called strongman, and it's supposed to do. Okay, strongman substituting humans again, and here's the new stuff. Simon, a mobile robot that is supposed to be a member of a crew, and this is Simon talking to Alexander Gerst. And again, some of you have heard that. There's a video on YouTube where they are having a discussion about emotions, and it sounds like Simon's emotions are hurt by Gerst, which is really interesting. So my idea is We don't want that. We don't want a robot that controls a crew. We want a robot that's part of a crew. And my university gave me 2 robots of this kind. This is a Now robot. I have both those robots. And I'm thinking about including those 2 into the dynamics of a human crew because they look human. They play with the idea of a cute child, and you can easily do research on how they would work as members of a human crew, not as human substitutes for what humans can't do, but for what humans can do too. So I'm interested to look at what properties humans ascribe to robots, what tasks robots get, how you care for robots, and how astronauts perceive the robot, or in short, what properties astronauts ascribe to robots. And to do that, you can use the robot as a recorder. You can do natural language processing and basically analyze what the astronauts tell the robot. You can do image processing and basically analyze what emotions the astronauts portray while they look at the robot, because the robot has a camera. And you can look at random interactions that way and observe how the astronauts interact with the robot. But you can also do the following. You can look at interaction based on cultural archetypes concerning robots. And those archetypes, how robots should be, often come from popular culture. Think Star Wars, think R2-D2. There's a brilliant article that describes why AI is so poorly received. That's because we want R2-D2. We don't want HAL. We want something that can relate to us in a way that is specific, but also very human. So my idea is, and I'm just working on that, to construct ideal types of robotic character, ask analog astronauts about their ideas of ideal types of robotic character, something that is done in sociology all the time, and then simulate that characters with the Now robot and analyze the way humans, how humans interact to that. So this project will be about observing archetypal assumptions, because there's a difference between a robot like that, Data from Star Trek, or a robot like that, Wall-E from the Disney company, or even a robot like that, who basically, through the way he is perceived, is scary in the beginning, but then manages to save humanity. So my idea is ask analog astronauts about their assumptions, about their childhood perception of robots, and then simulate those through the Now robots who are sitting down there, and then see how that works within an astronaut crew. And that is the future of my research, and I'm hoping to do that at the next MPOL that we're having. Thank you.
We are looking forward, so we are putting together the team towards the MPOL 3 and 4. This would be the last week of April and the first week of May. We have a number of candidates already. So this includes you, Michael, and now. Then and then we have another crew which is planned. So MPOL 5 and 6. This will be in August. At the time where we will have also a series of other activities like a space workshop at an analog training center, even some rocket and balloon launch. This is planned for August. So we have then 4 one-week campaign plan. Yes, so I think that
I've been teaching model rocketry at Christian schools in our area. So if you want somebody who can do religion and rocketry, I'm good for that.
That will be very interdisciplinary, and also the idea is that for the April bit, we could also help a bit in the build-up of the moon base, and that Agatha has shown us the new one, and installing some of the equipment and doing some work there. So I think that MPOL session was yes, very amazing, a great result, a great crew, mission support. We are a bit over time because so many interesting stuff, but I think that was great. And okay, let's go now to the EMIS campaign. So the IC's EarthMoonMars International Moon Base Alliance campaign. And I know that so some of you have time constraints. So Mark has asked to speak first. Is it okay? And then we have Anne Lotte that is also has prepared something. And I have also some recording that was sent by Anna Castro and by Sabrina. So let's go to Mark then on the report EMIS 3.
So I was actually part of EMIS part 3. So I was in Hawaii last January, just before all the lockdowns went in. So I will be presenting some of the rock hard science that we have done during our mission.
Mm-hmm.
And of course, rock hard science is a little bit joke because I'm a geologist myself. So the crew consisted of Michaela Musilova, who was our commander, Priyanka Dashrashkakati, his vice commander, Lucas Brasileiro, our space cowboy and chief engineer, Robert Heemskerk, he's also my brother. He was the rover's operations engineer, Kyla Edinson from Hawaii, who was in science communication, and myself. Yes, and we have some cool pictures. So very briefly about me, I'm Mark Heemskerk. I'm from the Netherlands. I have done several bachelors in earth sciences, in physical geography, geology, and geochemistry. And I was the lead scientist at EMIS3. So we go with a very nice effect. I hope the effects all come through. Of course, geology rocks, and it has been a lifelong dream of myself to do a lunar field work, such as we did actually on Hawaii, and to explore some of the lava tube systems that you can find on the lunar or Martian surface. Coincidentally, the picture that I've chosen here, this is Mordor. One does not simply walk into Mordor. So this is not a lava tube, don't walk in there. But the lava tubes that we have seen, those are pretty nice, and you can actually walk and live in there, or at least we hope. And I've been focusing myself on the magnetometry of the lava tubes. And overall, our EMIS3 mission was mainly focused on ISRU, in situ resource utilization. So for example, to build little concrete blocks out of lunar or Martian dust. Or another form of ISRU is to dig holes into, for example, here the glaciers, which we have done in the Matterhorn Glacier in Switzerland, or to even simpler, just use the whole structure that is readily available for you on the surface, or actually under the surface of the Moon and Mars, such as this lava tube. Yeah, so I've been focusing on lava tube homes, and they have a lot of good things with them. They will protect you from radiation. They will give some thermal insulation. They will protect you from micrometeorites. You will have very little to none of the regolith inside, which can also be very harmful for you as a human. But there's one big problem, and that is the accessibility. And as you can see, some of the entrances, or skylights as they are called, are quite steep, and thus not very safe to just simply drop humans in, especially not on the Moon or Mars, where some of these caves can be over 300 meters deep. So manual mapping, although it is very cool, you can see 3 of my fellow astronauts here on the lava tube on the right. It may not be the best option as one of the first ways to explore lunar or Martian lava tubes. And this was also one of the researches from our vice commander, Priyanka Dashrashkakati. She looked at several types of cameras to see if you can register some sort of depth, which luckily functioned both in well, daylight, but also in much darker pictures, such as the one here on the left. With her camera, we could actually see and also navigate a little bit to see where we could stand easily or where we would kill ourselves. Another way to try and explore lava tubes would be, of course, with robots, such as this tiny little 6-legged rover from the TU Delft, which is called Zebro. It is trying to come up the hill quite successfully eventually, but still it's not that fast, and you will still need some sort of connection to the surface with all kinds of rovers. And the project of my brother, Robert Heemskerk, who is here on the left. Give us a little wave. Yes, nice. So he worked with 3 different types of rovers. You can see a very big one standing on the bottom left, which is called Helelani from Pisces. Can I pause the video? Yes. So we also had 2 other types of rovers. This is the small EarthMoonMars rover, which was on tracks. And we also had a 6-legged rover, the Zebro, as I mentioned. So we had 3 different types of locomotion, and we were wanting to see if those rovers could cooperate and if they could work together to more safely, more efficiently explore. But again, you would still need quite different type of rovers here on the lunar or Martian surface. This is our commander, Michaela Musilova, giving us a wave here. So even different types of rovers, although very useful and very good help for humans, may not be a fully replacement of human exploration on the lunar or Martian surface. But you still have the problem of how to get into the caves. So I tried to do something with magnetometry. And magnetometry is something that's usually used to, for example, find golden coins in a riverbed or to find a ring on the beach. And it works on all kinds of magnetically conductive materials or metals. They will give a sort of a higher reading of the local magnetic field in the magnetometer. And because of all the rocks on Hawaii, but also the rocks on the Moon and Mars, or the basalts at least, where we have lava tubes in, are pretty rich in iron. The idea was that the only way to have a sort of a negative anomaly in the local magnetic field was to have an absence of rocks or a presence of a lava tube or another kind of hollow system, maybe built by aliens, but then it would still be pretty cool to explore. So that was the idea. And we tethered some astronauts on a rope, and we had a magnetometer from Geometrics flying small profiles over the ground to see if we could actually find this negative anomaly under the surface. And luckily, it worked. So as you can see in one of the results here, this line is the reading of the Earth magnetic field, and it actually drops down by almost 10 to 15% in strength when you are flying over a lava tube. So it works. Very, very briefly, next steps, geo-ice. I will tell a lot more about this tomorrow, but we will also try and construct an actual lava tube home inside a lava tube, which is located here on the left. I hope you can see my pointer. This is the Stefans Hedlier lava tube system in Iceland, Western Iceland. And on the inside, it looks a little bit like this, with hopefully some ice as well, just like we hope to find on the Moon and Mars, because water ice would actually give us very nice extra research opportunities, but also would help us with feeding our humans and our plants, and maybe even fuel our rockets. So that was a little bit of an overview of what we have done with MIS3 in the continuation of our research. Would like to thank all our sponsors, which are here on the bottom. And if you want to know more, feel free to send me an email at mark@geoice.com if you have questions about GeoIce or anything related to the science of MIS3. Okay. Thank you very much.
Mark, thanks for passing by. And so, and tomorrow we have a dedicated session on EarthMoonMars at 3 o'clock, and 3:30 we'll have a chill ice on Mars. So I encourage everybody to come and attend. Now, from the EMIS campaign, we have Anne Lotte that has put together a presentation together with Sebastian.
My name is Anne Lotte Weert. I was a crew member of the MS EarthMoonMars IMA High Seas 1 crew, which also went to Hawaii to do a 2-week isolation in the high seas habitat. So it already is some time ago, because it was back in 2019. So let me introduce you to the crew. We have Michaela, Sebastian, Niti, me, Josh, and Benjamin. So the scientific projects we did, they focused on microbial life in lava tubes. Sebastian did research about this. Yeah, so why do you want to study the lava tubes? Well, they give stable conditions for possible life on other planetary bodies. And yeah, if there is microbial life, they can leave secondary minerals. So therefore, we studied them. Yeah, I studied the hydrous alteration of the lava flows themselves. So why do you want to do that? Well, they contain clays, and clays they form in the presence of water, because the lava flows on Hawaii are analogous to the ones we find on Mars. They can tell something about the history of Mars and how there was water. And in addition, it can say something if there was or if there was no life on Mars. So first, the microbial life results. We find 3 types of deposits inside the caves. First, we found white powders, we found crystalline crusts, and we found coralloid speleotherms. The speleotherms, they look like this. They are composed of opal silica and calcite interlayered, and this can be due to microbial growth, but it can also just be due to hydrous alteration. There is a big discussion going on. And if you want to form these kind of deposits, it looks like this. There is meteoric water precipitating inside the basaltic rock. The basaltic rock gets dissolved, and ions they come out of the solution and form these type of minerals inside caves. Well, on Hawaii, we found those white nice powders inside the caves. But on Mars, we also have this picture from Curiosity, who found a similar type of powder. We don't know what it is because we do not have measurements, but it may be the same sort of material which can be formed by microbes, but we do not know for sure. And also there are some reflectance spectra from the minerals we sampled on Hawaii, and they look similar to the ones measured from orbit around Mars. So then the hydrous alteration results, we found different types of lava flows. Some are black in the top layer, some are more brown, and we find that over time the brown top layer increases, which is due to hydrous alteration, which you can see in this picture. Here, this one is the youngest flow. It does not contain any brown material on top. And if we go looking over time, the brown material increases, and it relates to hydrous minerals, which are represented by the blue pixels in the figure below. Those hydrous minerals, they form actually kind of in the same way as the minerals inside the caves do. Like in the caves, meteoric water interacts with the basaltic rock, which gets dissolved, and ions become into solution, and they precipitate as secondary minerals, which can be recognized in the field by the brown top layers. If we want to compare that to Mars, then we first have to look how the minerals on Earth behave. Well, if we put them in a diagram, the expected weathering trends on Earth, they are indicated by the arrows. If we then compare it with Martian data sets, we see that they do not follow the arrows, but there are minerals. So the minerals that are present, they have formed in another way, and it's not really clear at the moment how they formed. Also, the reflectance spectra of the minerals we found on Hawaii are similar to the spectra made from Martian orbit. So there definitely are hydrous minerals on Mars. And there also is water on Mars, but we do not know if we can say something about the microbes or Mars based on these data. So if you want to learn more about our mission, you can watch Space Drop on Amazon Prime, which was made by Josh, or you can listen to an interview with the radio, which is in Dutch. You can find it on their website. Or you can email me if you have any more questions.
Beautiful. So, yeah, so I had also some presentation that was sent to me by Anna Castro and Sabrina.
Hello, everyone. My name is Anna Paula.
Hi, everyone. My name is Charlotte Pauwels.
And welcome to this virtual edition of EarthMoonMars workshop. Today, we're going to talk briefly about our experience as analog astronauts with MIS2, which was the EarthMoonMars in High Seas. This was the second edition. And we just present briefly the research we did and other activities. So our team was mainly women. Our mission commander was Michaela Musilova. I myself, I was the chief engineer. Charlotte was a crew physicist. Sabrina and Ariane was a crew engineers as well, and also space architects. And the only male on the team was Joseph D'Angelo. He was our chief medical doctor, and he was a great addition to the team. Our mission was a lunar simulation that happened last year from the 8th to the 22nd of December on the high seas habitat in Hawaii.
So our main base was located at Aztec in the Netherlands, where also our remote control stayed around during the mission itself to support us with rover and drone tasks. But the mission itself took place, as Anna said already, in Hawaii in America. As you can see on the map, it's quite a distance. So we flew there from different countries. So Anna is from Brazil, I'm from the Netherlands, but we also had people from America and from Germany and from Vienna. So we stayed at the Blue Planet, and then we went to Mauna Loa, which is a volcano at Hawaii, where the habitat High Seas is built on, where we conducted the analog astronaut mission and its research.
All right. But just to talk briefly about my own research and activities as a chief engineer, I was mainly responsible for the habitat equipment, that meant power systems, solar panels, inverters, generators, everything inside the habitat, and also to ensure nominal operation of our EVA equipment, which stands for extravehicular activity, which is everything we have to use when you go out of the habitat, and we do that for many reasons that we talk about in a minute, and also to check all this equipment before and after we leave for an EVA and go back from it, and also to gather the feedback from the team to see if all the communication systems were working, if everyone was hearing each other fine. Also, I would need to provide mission control with daily engineering reports myself as the chief engineer. I also operate drones and rovers, and when we had time, we need to support others members' research projects. So for the small rover, it was shipped directly to Hawaii, and then I assembled it there. Of course, we had some difficulties on the way, but the rover was remotely operated by a remote port in the Netherlands while we were in Hawaii on the mission, so that was really nice. The drone itself has been around with us for some time now, and it has provided some amazing footage from the mission, but also is very helpful when you're doing surveillance of the area and when you're trying to find lava tubes around the habitat. It was quite useful. Other engineering tasks mainly comes from troubleshooting, and you have to be creative in the matter. Here we are using toilet paper to try to find the leak. And that also we needed to do some EVAs just for troubleshooting. It was very hard, but also quite fun.
So as part of the task of being a crew physicist for the team, I did mostly some research about food development on the moon or on Mars. And we're really interested in how to develop a greenhouse system that can use in situ materials, such as the soils that are present on the moon or on Mars, and use it to grow crops on. So we were collaborating with Food for Mars and Moon and Wiegem Wameling for this research. And another part of the research was to see how the radiation environment, for example, on the moon or on Mars, which is quite higher than here on Earth due to the lack of an atmosphere and low magnetic fields, how this would influence the crops itself. Like what kind of mutation would come forward, or what would you observe, or is there enough contamination that you need to protect the crops from? So this was quite interesting to test. Another thing is that we use different percentages of compost to add to the soils to see how the crops grow, and that we need to bring less material from Earth to reduce the payload for the rockets that also can be used for medicine or other important materials that we need to bring to Mars. So it's very important to look at what you have on those other celestial bodies and to see how you can use that to set up your base over there. Another important research that we did was the diet and nutrition of astronauts. So what kind of influence does a different diet have, or different nutrition values have on the astronaut and how it performs during the day? And this research was conducted with Joanna Chapuis, a dietist from France, which was quite an honor to work with her. And we made like a dietary plan with the dry freeze food that we had available at high seas. So we got like different meals during the day with enough nutrition so that the astronauts could perform correctly. But another important factor that we came as a conclusion of this research is that cooking those dry freeze materials, actually cooking the materials and establishing like a nice dinner meal for your crew and eating together as a social gathering moment during the day is really important for your crew bonding. So this was a nice observation, and I think it's really important to see how important it is for the astronauts to have that social aspects to stay mental stable, actually, especially in space.
Yeah.
So another part was the lava tube exploration, of course, because lava tube exploration is very important when you go to the moon or Mars, because there are lava tubes present there. And these lava tubes can be used for protection against radiation or meteorites, or can offer some already some boundaries where you can place a habitat in. So especially in the early moments of developing a habitat, it would be really important to see if we can stay inside a habitat and construct a habitat inside a lava tube, actually. Another important thing is the geology of lava tubes, how they are formed and how they are present on the moon and on Mars and on Earth, and what the differences are between them. But also life. Life can actually be present in lava tubes on the moon and on Mars because it is protected from the harsh space environment, actually. So for this mission, we conducted multiple EVAs inside some lava tubes that were nearby the habitat, which were around 30 minutes to 2-hour walks. So on the left, you can see the team actually exploring, making our way over the lava flow itself to find a lava tube, which were quite difficult to find. So drone, where Anne was talking about, could be really useful. And another not so cool EVA, which was pretty important, was dropping our garbage, such as the poo and the pee, to another facility. So this was also conducted during an EVA. And our commander Michaela Wisilova, she was amazing with this. She helped and assisted so much with this difficult task. So total respect for her.
All right, and another important research that was also conducting during our mission was about space architecture and 3D printing. Unfortunately, Sabrina and Ariane cannot be here to explain better. But basically, we teamed up with a 3D company MakerBot, and they provided us some amazing 3D printers And that way we can use additive manufacturing during our missions. And that is very useful because as an astronaut, when you're actually going to space, to Moon and Mars, you have limited amount of space and of course storage and also the weight that you can bring. So you cannot bring all the tools you need, but if you have a 3D printer, you can actually just print these on the moon. And even more exciting, you can use insider resources, you can use the materials available there to print this for you. In this case, we use the normal printing plastic, and we use that as for some tools for our equipment, but also you can use that for leisure and as personal equipment. I mean, like sometimes you want a souvenir from your family or something that reminds you from Earth. And if you cannot bring in, you can also use the 3D printer for that. And our mission, it was near Christmas, so use that to print some Christmas decorations, some cookie cutters, and also some Christmas trees, as you can see here. And that really added up to the overall value of our mood, and also to bring the crew together as a team. Another important study they conducted was a semi-private room, because besides from your sleeping quarters, everything else, of course, in the toilets, everything else is shared on the habitat. But then Sabrina and Ariane, they created this semi-private room where you could chill out during the day, just if you needed some 5 minutes alone from the crew or just to rest a bit, to clear thoughts. That was very helpful. And another experiment they conducted was about the color study on the habitat. And the first week, the whole habitat was covered in white, and we were not allowed to wear any colors. So for a whole week, everyone was kind of grumpy, as you can see in the picture. But then on the second week, they brought the colors back, and that also helped improve the mood a lot. Of course, we used the Christmas decoration to brighten up the mood and everything. And they perform everyday psychological surveys that we had to answer every day. It was kind of exhausting. But then they found out there was an overall improvement of everyone's mood when the colors were introduced back to the habitat. And there's an important part of space exploration that sometimes we forget to talk about. And about the challenges and outcomes of the mission, of course, when we're very busy, we have so much going on, and with troubleshooting and everything, is a very demanding daily schedule. So we try to follow the daily schedule of 24 hours. We try to sleep at least 8 hours so everyone is healthy. But of course, we also have our daily chores, we have projects, we have other tasks, and we also need to exercise for an hour a day. And that makes the days go by so fast. This is a challenge. Another thing is the distance and isolation. For troubleshooting, for limited communication windows, we only had a few hours a day to talk to mission control and remote support. And if you have any urgent matters to address, that can be quite challenging, because first you need to figure out for yourself, because help is days away from you. So that's one of the challenges. And for outcomes from the mission, we provide some feedback and improvements from the equipment and the habitat itself, as you can see here, some examples. And also we try to create protocols for further missions, so their missions can be, they can focus on their own areas of research, but we can also create protocols for space exploration, and for eventually when we colonize Moon or Mars, we have some idea what's important and what's not. And that's it. Thank you. If you have any questions, you can reach out to us and be happy to answer them. And also, of course, we need to thank our sponsors. We are here below. They made this mission possible, and without them, we wouldn't be able to go to the moon for 2 years. So thank you.
Thank you, everybody. Have a good day.
So Julia, if you want to describe what you're doing, introduce yourself, but also how this could contribute. Yes.
Sure. Can you see my screen and can you hear me okay?
We can do well.
Excellent. So hi, everyone. I'm Julian Villamason. I'm 35. I want to talk about 3 different things today. But first, a couple words about my profile. I'm an engineer, but I've been working 10 years in renewable energy in the sales and the business side of things. But I'm also a professional pilot, and I'm also a developer in terms of apps and things like that. So what do I want to talk about today? 3 things: zero-G flight, Moonscape, which is the startup I'm working on at the moment, and the MDRS mission that I'll be doing next year. So looking at the first item, zero-G flight, and this is stuff that I've prepared for the ISU SSP program that I attended last year. So just reusing some things here. The state-of-the-art parabola control today is using 3 pilots, really. 1 for roll, 1 for thrust, 1 for pitch. And you can see the little bands that they use here to control roll, which is quite interesting. So what they can yield is a really good quality for the parabolas, I think, considering it's manual. And that's if you add 30 parabolas at a time. On the right side is the zoomed view. And the blue bands is outside of the contractual margin, and the white band in the middle is the contractual margin. So they do stay within contractual. But I think it could be done better. So my proposal was to do an autopilot that would manage everything by itself. And this would be better with an electric aircraft. So I believe that the advent of electric aircraft and digital control can help perform better parabolas. So I'm hoping to work on this in the future when electric aircraft come online. This is not the case today, but it's coming very soon. This is what I think it would look like with an autopilot. I've made an app that I use on my watch when I fly to fly parabolas, for example, Mars, Moon parabolas, or zero-G. You can get this app for free on the Garmin website. Considering time, I'm moving on to the next topic, which is Moonscape. This is the startup I'm working on. This is a startup which goal is to launch a constellation of satellites around the moon in low lunar orbit. And this is to observe the moon at specific sites for our customers. The first use case is to do landing site surveys so that customers who will land on the moon, those are those who have landers and rovers. Those who will land can inspect the landing area better and can find which side they want to land on. The second is asset monitoring. When you start to have a lot of rovers on the ground and more, then it's important to have not just a view from the ground, but also from top. And then there's other opportunities, such as rover path planning and things like that. I'm not going to detail this now. It's just to give you an idea. This is just an idea of what the satellite would look like. This is actually LRO. We want to do a better kind of LRO with higher resolution, maybe more wavelength, like in the spectrum and things like that. We want to start with a phase 1 of sort of a minimalist spacecraft that has the bare minimum to function and to start sending pictures to the customers. The second phase will have more satellites and higher performance if we see that the business is actually working out well. The third point I wanted to hit is the MDRS mission I will be doing next year with the team. This is the team we have currently. We are multidisciplinary, so it's a great team actually. You can check out the website here if you want. The 1 or 2 points I wanted to make here is that we just finished a call for experiments. So we asked people in the Mars or Moon, I don't know, I don't want to say industry, but the interest groups to propose some projects. And this is the result we've got just last week. You can see on the right side, the ISRU got a number of proposals, the highest number, then robotics, and then life support. The reason I mentioned this is just in case you guys have any advice, or even if you want to propose something, maybe we could still accept it, although we closed last week. But that's it. The mission will be in December 2021. And that's it. Thank you very much for listening. I think I did less than 5 minutes. If you have any questions.
Yeah, beautiful. Yeah, excellent. Good for the timing, for the content, diversity. So we are looking forward. And all the aspects also, yes, to have you on board the EMATA, but also to look at some of this MDRS 2031 to provide experiment or investigation also, like following what we are doing in other campaigns. That's good. And also good luck for your startup business as well, which is also connects also with what we heard at the beginning, some data analysis, and then we could also see what is needed for the future in terms of a small satellite for the future. Okay, so thank you very much. So this is today a forum more to to get to know what everybody is doing in a kind of a snapshot, and we will then try to find a way to have a further discussion in the normal Your Own Mars channel, plenary, and a subgroup. So EMATA is meeting every week, so we have a slot, so you are welcome to join in either as faculty or also as a users, and you can also put some of your questions. So not to drag too much in time, we'll go very fast to the next point. I had, in fact, put some time estimation on that, but we were planning to spend much less. So there is a next point on, so EMATA, please contact Nancy if you want to join the group for discussion and for being faculty or for being astronaut candidate, and then we will put you in the loop. Now we had a point on EarthMoonMars. Tomorrow we will have a dedicated session to EarthMoonMars at 3 o'clock. And then here I just put that in case there is some EarthMoonMars colleague that are not available tomorrow. But the latest news for EarthMoonMars, so we have a number of events. We have this event organized at the Leiden Observatory, and we'll have a closing session on the 19th December. And we look to make a kind of virtual closing with all the artists making some recording of their work. And we may have also some music recordings. So we are trying to make a compilation of space moon Mars music that could be broadcast at this opportunity. Another interesting EarthMoonMars event just took place today. It was just before our workshop from 2 to 3 o'clock. There was a premiere of a global science opera, a project with more than 15 classrooms all over the world on the theme of energy, energize. And we managed to insert a little scene from ourselves into this global science opera. I will give you the link where we had this recording of this moonwalk that was performed in the Nordwijk Space Expo in front of a lunar lander. So we have a number of initiatives, but we are going to talk a bit more about EarthMoonMars later. Now, about SGSE, so we have started at the Space Generation Advisory Council a program which is called mentorship. So we have established a relation. So I am the mentor, but I have a number of mentees, but which are quite advanced in their career. And I think that I've invited them to introduce them shortly, in 1 or 2 minutes, so that we know them, but also we could enhance some relations with the Space Generation Advisory Council. That's a community of more than 15,000 young professionals all over the world. So maybe I could start, who is still there? So we have Feven, and we have Armando, I see in the list, and we had Matesh just before. But yes, Feven, if you want to introduce yourself.
Hello, everyone. I'm Feven. I'm from Ethiopia. I am a recent graduate of Astronomy and Astrophysics department from Ethiopian Space Science and Technology Institute in MSc level. In undergrad, I graduated in electrical and computer engineering. And in another undergrad, I studied business management. Currently, I'm seeking for PhD opportunities. My MSc research area mainly focuses on low mass white dwarf neutron star binaries. Thank you, and I'm happy to be here. Okay,
yes, so thank you. Good to have you. And you're also a point of contact for Space Generation Advisory Council in Ethiopia?
No, I am a member and I participate in the outreach programs here.
In the outreach program, yeah, okay, excellent.
Yeah.
And so there is also a plan for next year in February of a big Space Generation Advisory Council workshop, Africa. And okay, I know that some of us are invited to go there, so we may meet there, hopefully. Yeah. Excellent. So, and then we have Armando. you want to introduce yourself.
Hello, everybody. Hello.
Yeah.
I'm Armando. I'm from Italy. Until the end of July, I worked at ESA as a trainee of the Member States Relations and Partnership Office of the Strategy Department, where I dealt with a daily activity of space policy monitoring, space business monitoring, and also elaborated some analytical reports on specific topics and documentation for the ESA General Director meetings with the Member States delegations. And I also gave my contribution to the ESA catalog of activities for the United Nations Sustainable Development Goals and for the internet pages maintained by the office. Later, during my internship, I became the team leader, managing common projects and tutoring new trainees. Before my experience in ESA, I worked as a teacher of law and economics in high schools in Italy. I recently participated in the International Astronautical Congress 2020 Cyberspace Edition with a video lecture and a paper titled Adaptive Governance, Space Resources, and Moon Village. My background features master in international relations, another master in European politics, and another master in space institutions and policies organized by the Italian Society for International Organization, along with the Italian Space Agency, for which the final thesis was about the return to the moon. My interest for the space sector is across the board, but obviously taking account of my background, it focuses on space policy, space law, and new space economy. And at the moment, I'm looking for the next step in my career. Thank you.
Excellent. So it's good to have you. So you're an example of yes, a dimension that we would like to also develop. So new space, you know, I'm more old space, but I'm trying to innovate. We had some an innovator like Hank Rogers, which was with us, Julien, and so for our project, you see that they are mostly we have project-driven activities, but at some stage we really need an umbrella where we need also to have a good public support, political support, economical support. So we are business aspect. So we are looking as well as a way to boost some of these areas. So in order to have some sustainable funding for the people doing for their work, getting also eventually PhD grants, getting also some money for service that we could provide. So it's nice to have also some people like you that could also advise us on some of these aspects. So anybody else from the SGSE mentorship group? So Matesh, are you still here? You mentioned he had to leave. We had also Selene. She had to leave because some of them are on completely other time zones. We had one on Canada, we had Saudi Arabia, and we had, but Italy is still with us. That's good. So that's general things about SGSE. We want also to advertise that we had some collaboration with the SGSE. Actually, at the beginning of the EarthMoonMars group, so it was about 20 years ago, we created a Moon-Mars exploration group at the Space SGSE. And this Moon-Mars group partly was also helping for the beginning of our EarthMoonMars activities. And we were organizing Moon-Mars workshop at each International Astronautical Congress. So that's lead us to another point of the agenda, which I wanted to discuss shortly, the point on networking, funding, grants, industry partners, business, startup, and ESA Lab. So this is, we are really looking now to go a bit consolidate, the way we do our activities, where we secure funding, also where we are able to write grants where we can be associated to partners in the industry. For instance, we have an example of MPOL. We had a number of sponsors. For instance, Roxana was able to find a sponsor from Aquavia, and we had other sponsor for the 3D printer. We had a sponsor for various equipment we were testing. We had Ariane Espace also sponsoring us for participation in the Hawaii campaign. So we want really to develop this, and actually now within the EarthMoonMars, I'm looking to hire part-time a kind of business and marketing manager that would really support us in all our activities, and also somebody that could help us to write research and funding proposals. So if you know some that could help in this task, or also if you know maybe some master business students that would want to help in this regard, please put them in contact with me. But at the moment, we need also to find some people that have the interest to develop in this area. Anybody has a comment? So I think that in the group, so a person like Julien has a great experience because he had his startup, is very innovative. And we are looking also at ESA, we have this business incubation center, and we have worked with them already more than 10 years ago at the beginning of the EarthMoonMars program. So we are looking towards making actually a proposal to the ESA business incubator at the beginning of next year, covering the different areas actually that you have witnessed today. So we kind of, we call it Earth Spaceship Laboratory for Astronautics and Business. So ESA Lab, and also looking at to have some ESA recognition for the various activities we are conducting. So anybody has some comment on this? So here's the idea in practice is to put a proposal where we identify in various institutions. So it could be, for instance, university institutes like the IPSA, could be Analog Astronaut Training Center, it could be various also small companies, and to make a collective network proposal, what we describe our ongoing activities, and we ask for support for the next years to consolidate them. Good. So anybody has a, yeah, we could also involve Canada, Amanda, yeah, because you have also actually created a structure like this in your university, so we could also show that we are connected with projects all over the globe, and already showing that we are working together. So it's not only artificial way to get some new money. Yeah. So that's for the networking. So look around, and if you have some business people, but also interested by space and exploration, you can direct them to me. And also I have a bit of a grant. You know, we created this Young Lunar Explorers grant, actually some 20 years ago, and every year we give some of this grant in other various areas. And this can be also recognized in the curriculum of a young professional. So that was on networking and funding. Other question, anybody has a lot of money to bring to the table? We had some good collaborators, like you just met Hank Rogers before. Hank Rogers made quite some good money because he's the owner of the right of Tetris. But he used his money, he invested in sustainable energy and also in exploration. So we were lucky that he really funded a large part of this moon base in Hawaii, and he allows us to collaborate. So making use of this facility at a lower price, and in exchange we perform research. And so we need also to find a few similar profile in Europe as well. Yeah? or in other countries. Okay, so that was for networking. Then we have a report from the communication working group.
Hi everyone, this is Ana Castro. I'm speaking from Brazil. I'm sorry again for not being able to be there live with you on this workshop. And today, now I'm representing the communications team. I will share a little bit about our work, what we do, and a bit of the highlights that we did this year. So our team today is comprised by many people. Sabrina is our team leader and she's leading us in these amazing projects. We also have the collaboration of many members that later they rotate to other areas or they're only with us for a certain period. And what we do is we mainly produce everything that you see and read on our social media and channels. We also and maintain the website and social media for EarthMoonMars. We do outreach for other space events, not only for EarthMoonMars, and also space-related conferences. Of course, we also respond to the media inquiries, maintain EarthMoonMars media kit. We do a little bit of public speaking when needed. We do live and in-person events. We help organize conferences and workshops like this one, and we also hold weekly meetings where we discuss important matters, and also we assign tasks and we have fun as well. So a little bit of this year's highlights. We were able to produce updated newsletters about the events that happened the past month or a few weeks, what was coming next, and also a little sharing experience of our members on different missions, for example, the Chill Eyes mission. So it's a very nice thing to subscribe to just to keep up to date what's going on with EarthMoonMars. We also created the EarthMoonMars events calendar on Gmail, where you can see all these events as well, just to be more visual, and you can also just put on your cell phone and then you know everything that was going on with EarthMoonMars. You can just subscribe to our calendar by typing this email address web@earthmoonmars@gmail.com, or after, if this PDF is shared with you, you can just click on the link below, and then you'll be able to see all the events coming up. We also did some pretty exciting live coverage of important events. One of these was the Perseverance Mars rover launch. So it was a big thing throughout. And us at Bernard and other experts, we do little talks commenting about the launch, what was so important. It was very exciting. And now recently we just added the TED talk by Anna and Elisabetta. They collaborate with us with the EarthMoonMars and Moon Gallery, and it's very high content, and I highly recommend that everyone subscribes to our YouTube channel. It's just type EarthMoonMars EarthMoonMars, you can see all of it and more. We also did some live events, in-person events when the corona restrictions allowed, of course, respecting all the local rules. Sabrina and others, they organized the Vienna workshop for space habitation. Of course, we had the EarthMoonMars collaborators, and it was a huge success. We had great feedback, and maybe we'll make it again. And we also established our EarthMoonMars website. Priyanka was very helpful on that as well. And there you can see the contents of what's going on and past missions and what is EarthMoonMars and more. And we also have all the social media on Facebook, Instagram, LinkedIn, and YouTube. You just type EarthMoonMars, you'll be able to find us. Please follow us as well. And that's it. If you would like to get involved, just send me or Bernard a message, and then see, and then we'd like to know how you could collaborate. Of course, we welcome any feedback you might have so we can improve the communications section. And that's it. Thank you.
So that was for communication. Now, I also circulated but a list of workshops that we are planning for the next year. So hopefully they will be presential. Otherwise, we can transform them into virtual. But so we have one plan in February in Toulouse, still, hopefully. Yeah, so you want to make a comment, Roxana? You can unmute, yes.
Yes.
Yeah.
So hopefully we will organize it. We don't know yet. We have to discuss it again.
Obviously, but in principle, okay, we have some.
For now, we're locked down, so
yeah, so we are.
Everything is closed.
So maybe in the worst case, we still keep the time.
But online.
And we do an online workshop, and then we do a big one later. Then
Okay.
also one workshop which was planned in Marseille-Nice area in the beginning of March, where we will have a visit of some observatories, Marseille, Haute-Provence, Nice Observatory, but also we'll have a visit of a moon base which was built in the 70s on a plateau, and which also has a big telescope of 1 meter that we can use. So we are planning, we are doing that in collaboration with Marseille and Nice Observatory. So still we are scheduling this expedition. And then we have an event planned at Paris at the end of March, 21st, 25th of March, corresponding with the International Astronautical Federation general meeting. We have all the committees, so it's I would recommend if some of you can come, that's a good way to meet some of the, there are 25 technical committees to get to know some of the big shots in the domain. And then we have our campaign that MPOL, and we are also an event we are planning in Torino, Padova, 14, 16 of May. So this I put all the dates. I want to end with publications, and I think this was a point that Agatha mentioned. So we have a number of conferences that are coming up. In particular, a very good one is the Lunar Planetary Science Congress, and there we should make some 2-page abstract. Each of you as first author, so I sent also the information by 20th of December. We should try to get this together. And then there is a series of events more for abstract due in January and February. And now on the point of articles, we have been asked by some reviews, some article to put together a EarthMoonMars special issue. And they are allowed to give me some free publishing in area, because I will do some task as a guest editor. But also we are going to put together a little grant for an assistant guest editor that could help, to chase all possible authors from the group. And so I have also a bit of money that I could give to, one of you that is willing to help me as a guest editor. And so we will now, after the workshop, because now what each of you are working on, we'll put together a list. First on abstract, we need to propose for LPSC. That's easy, that's 2-page. And after a possible set of more consistent papers, we could put in a serious journal. So that in short, where we are with this article publication. So that's covers all the subtopics that we had on our agenda. So we have a bit half an hour beyond, but I think we had so much result from the campaign and from the data analysis that we went a bit beyond. So in terms of a wrap up and action, I think I will put together a list and a little summary of what you have done. We are looking for a volunteer to write down some summary of today's workshop, maybe like a journalistic perspective. So, and I realize also that there are persons that we didn't introduce. Esther, we want to give you the floor for 1 minute to introduce yourself.
Yes, I'm Esther. I'm a fourth-year student at the VU Amsterdam, and I'm currently doing my master's in geology and geochemistry. And my interests are mostly in planetary sciences and in the exploration of Moon and Mars. I've known Mark Heemskerk, like he's in my classes as well.
Okay.
So I texted him because he had this article in the newspaper about him going to Hawaii. So I texted him, well, how did you get there and why and how? And I'm interested as well. And then he said, well, I'm currently in this other project, which is chill ice. So maybe you're interested in that. And I was like, yeah, I'm interested. So I'm now part of the chill ice team since a few weeks. And I'm probably gonna concentrate on the subsurface geology in Iceland around the lunar tube.
Okay, excellent. So, okay, so yeah, Roberto is there. So I've mentioned that we had an initial plan to organize an event in Torino around 14, 16 May. So these are all the baseline dates. I have to say that in the meantime, I received also an invitation from Milano, so a group which is doing architecture and also fashion, space fashion design.
Oh, really nice.
And actually, she has flown some fashion on space. So, and when we had a Moon Gallery exhibition at the Design Week of Milano, she came us and some of our students worked with us. So now we are really looking forward first that to have this COVID gone.
May.
And then do a nice expedition between Torino, Milano, Padova. We have also some invitation in the middle of May, just before we go all for Iceland. Some of us will go.
The full Italian week.
Yes, we are planning an Italian week. So we are.
Very nice.
Yeah, that would be nice.
Okay. And so we do it in a kind of expedition format. Where we go, we give lectures, we visit places. And
anyway, you can keep me in your email with every organizer so that I can manage maybe.
Yes, that's exactly. Yeah, excellent. Good. So I think that's okay. We have the group of survivors here. That's good. Good to know. So and I think that everybody had a chance to speak. I think today. So we did I think the record of a number of speakers we had all over for one of our EarthMoonMars workshop. I think this format with 5 minutes. Maybe we could be a bit more stronger on the time, but I think it was great. Everybody had the chance to speak, to show what they do. And I think we will try also to organize another type of workshop, virtual workshop, maybe in January already. And tomorrow, so we have this EarthMoonMars and this Iceland Chill Ice session, but that is really organized by the Chill Ice team. So I encourage you to attend. So otherwise, so any final comment? Christian, anything fine?
Yes, I hear everything. And Christian or Christoph, I don't know. I'm not sure.
No, Christian.
You mentioned me. Okay. I'm really excited of that situation. We came up.
Okay.
And I think.
And you see, we have also our exoplanetary scientists. They are big survivors. They are still with us. They were at the start and they are now.
Yes.
So how was it to go through all these activities, to listen to what the others are doing? Christoph and Ike, any concluding remark?
Yes, it's very nice to see the whole group, all the projects, all the variety. Yeah, it's very, very nice.
So that's why I say we are like an Earth spaceship laboratory with the different research activities. And so we are going also to present this way that we have a diversity of activities, and we will also look for also support so that we could also eventually get grants for PhD students and for funding campaign and so on. Good. So Amanda, any perspective from Canada?
So yeah, in Canada, it's pretty good. We are having our preliminary design review for our first project. And our second one, we currently have a second research thesis that has enrolled in the physics department for our second space health project. So just to give everyone an overview, our first project is looking at the human.
Yes.
Hello? Yeah, it's looking at the human immune response in microgravity. So it's looking at how genes have certain upregulation, downregulation after being exposed to extreme G-force and microgravity. And our second project, we are actually going to be 3D printing the human heart, the aorta and the ventricle in different dimensions, according to the effect of microgravity and the pathologies like aortic regurgitation, then also aortic aneurysm. And we're going to be putting it in an MRI machine on Earth. And then when it goes on a parabolic plate, we take an ultrasound machine to do a similar analysis.
Oh, you know, I was involved in a contract, actually. I was the chairman of the board of a contract to print organs on the moon.
Oh, okay.
Yes, so we worked with, so there was a competition, and one company got it, and it was a group from Bremen and OHB.
Mm-hmm.
So at the end, they selected the skin as an organ.
Yeah, okay.
That's the simplest one.
Pretty important.
Yeah, but eventually, another group managed to print a heart, but a miniature heart.
A miniature heart, okay.
A small size heart. And they printed the heart, and the heart was beating.
So they attached it to a pump, basically?
Yeah, so they
okay.
could,
That's really,
but,
yeah.
But the main contract we had was this tissue production. So in case of injury on the moon, you can 3D print.
You can implant something and it's going to grow. Or 3D print it. Okay.
Yeah, so that's something also. So now for all of you, okay, we have this plenary like marathon, but we could also organize more topical workshop, you know, on a specific topic, a shorter duration. And we could also, for instance, we could do an ample workshop, we could do human medicine, and we could have a series of events like this, and that we could prepare. But when I see the quality of what was presented today in your 5 minutes talk, this was, I think, great to listen to. Roxana, do you want to have the last word for Commander Roxana?
I'm not the only commander here.
Ah, yeah, Roberto also, Roberto, yes.
Yeah.
Yeah. So, okay, so next step for
us, the outreach of all the research that we did during our missions.
Okay, research.
We have Christian that is already working on articles and abstracts, and we will do the same in December. So yeah.
Good, excellent. So I think that I may see some of you tomorrow. So tomorrow at 3 o'clock we have EarthMoonMars and Chill Ice. So enjoy the rest of your dinner and evening. Take care. See you.
Bye. See you tomorrow.
Bye.
Bye.